The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone, and welcome to the 4th annual workshop on climate and atmosphere research and innovation in the Eastern Mediterranean and Middle East. This workshop is organized by the Climate and Atmosphere Research Center of the Cyprus Institute and supported by the EMME-CARE and Edu for Climate projects. My name is Eleni Zinonos. I'm a project officer here at the KRC, and I will be guiding you through this workshop. We have an exciting program with about 30 talks reporting on the latest research and innovation findings in the field of atmospheric sciences in the EMME region. And it's great to have so many of you here with us. Many thanks to all of the presenters and chairs for making this possible. Throughout the workshop, you will be able to submit your questions for the oral presentations in the chat. Your questions will be reviewed and passed on to the presenter by the chair. And due to time limitations, though, we might not have time for all of your questions, in which case we might be able to pass on your questions to the presenter after the end of the workshop. We should also remind you that this workshop is being recorded for monitoring and reporting purposes and for the promotion of future events. As a reminder, each presenter will have 7 minutes for their oral presentation, followed by 2 to 3 minutes for questions. We do have a full program, so a kind reminder to stick to timings. I will be keeping time, giving presenters a reminder when time is up, or if they're running late to ensure we keep the flow of the program. Again, please remember to submit your questions for the oral presentations in the chat. And without further ado, I will pass the floor now to Dr. Shabrel Afif, professor at St. Joseph University in Lebanon and adjunct professor here at the Cyprus Institute, for an introduction to today's workshop. Professor Afif, the floor is yours.
So thank you, Eleni. I will share my screen. Eleni, can you please just confirm that you can see my screen?
Yes, I can see this.
Yes, okay, great. So thank you, everyone, and good morning, and welcome to this fourth online workshop on climate and atmosphere research and innovation in the Eastern Mediterranean and the Middle East. So like the previous years, so this workshop will tackle different topics related to studies on air pollution sources and impacts, modeling, atmospheric dusts, climate and weather extremes, and instrumentation. So first, I would like to thank the members of the scientific committee, so coming from Europe and also the EMME region, for their contribution and preparation of today's workshop and topics. So you can see their names listed here. And I would like also to thank the organizing committee, so Marina and Eleni, for their support and efforts in making today's event. Thank you a lot. And then I'm also happy to and delighted to share that this year's workshop gathers almost 240 participants from 49 different countries. So last year it was we gathered participants for 47 countries. So we keep breaking records, and so from different regions, from Europe, Asia, Africa, South America, and North America. And practically this shows the success of these online workshops that we're conducting, that we have been conducting for the last 4 or 5 years. So, of course, the participants are professors, academics, also masters and PhD students, and also industry experts coming from both the private and the public sectors. So for this year's workshop, we decided to focus on oral presentations exclusively, with no quick pitches, in order to have more detailed study presentations. So this changed from the last 2 versions of the workshop. So hence we have 27 presenters from 9 different countries who will share with us their knowledge and experience, and I would like to thank them in advance for this day that I'm sure will be very fruitful. So without very further delay, I would like also to thank you all for attending this workshop, especially the keynote speakers, so Dr. Gaël Ouzou and Professor Jean Siard. I would like also to wish a quick recovery to Dr. Ala Hawish, who wanted, in fact, to attend, but for health reasons, he wasn't able to. He won't be able to be present with us today. So I would like also to remind you that once again that this workshop will be recorded, so you will have the chance to go back again whenever you want and see and listen to the presentation. So there will be a repository on the web page for the previous, like for the previous years, but also we'll have the different presentations also from the different for the different years, the previous years. So you can also access them again. We will be sharing with you the links. So I wish you a successful workshop and a great day ahead. And thank you all for your attendance and your attention. Thank you.
Thank you, Charbel. We're waiting now for Professor Siard. We'll just give him a couple of minutes. If not, we can move on to the first presenter, but I think he's here. We just need to be able to share the presentation. Just bear with us a couple of minutes and we'll sort it out.
So Dr. Rami Farra will now be our chair for this session. So practically our keynote speaker will be Professor Siard, and then we'll have the oral presentations. So Dr. Rami, practically the floor is yours to chair this session. Thank you.
Thank you very much, Charbel. Can you hear me now?
Yes, we can hear you. And you can turn the camera on as well.
And the camera is, I hope it's on now. Yeah. Well, thank you very much, Charbel and colleagues, for your sustained effort and this excellent annual event. And glad to see it on its fourth year, and I hope it continues for many years to come. Good morning, everyone. I'm very pleased to be taking part in this event, and I'd like to thank all the speakers for this session that will focus on atmospheric dust, climate change, and weather extremes. The session will start with an invited talk by Professor Jean Siard from Cyprus Institute. He will have 20 minutes. And this will be followed by a series of 7 talks. Each will be 10 minutes long. I'd like to thank all the presenters in advance and ask them to stick to time so we can make the most of this. Thank you all very much. And if John is ready, we can hopefully start.
Jean is trying to set it up, so let's give him 1 more minute. Hopefully he will be ready in a minute or 2.
Okay, thank you. Yeah, I think the session is very wide in scope and range. Fantastic talks are lined up for us. So I hope all of you will have something to enjoy and keep you interest. We have talks on UOV observations, others on chemical pathways and fire plumes. And then we have one on dust over Cyprus. And then our next one will be on heat wave metrics. And then we have a case on CMEP-6 in the Middle East, precipitation projections. And then we have a case study on the extreme rain event and convections in the UAE last year, 24. And then we will end with talk on the heat risk at Hajj season 2024 and some future projections. So I think we have an excellent array of talks covering the topics of dust, climate, and extreme weather in our region. And I hope that they will all be informative and will hopefully incite a lot of questions in your minds. I'm trying to fill up the time, the air time, as they do on TV. I don't know if I'm doing a good job or not, but at least I'm trying. So we'll just wait for a couple of minutes, hopefully for John to be ready, and we'll take it from there.
Dr. Rami, if you want to launch the first presentation, if the presenter is ready, maybe we can do that.
Yeah, as Kenneth, is Kenneth online and ready to start? That we could start with the first 10-minute presentation by Kenneth Chorn from Cyprus Institute. Can you hear me, Kenneth? Are you online or not yet? No?
I
Okay.
can see Kenneth by there, but Eleni Dobru is online, the next person, so maybe we can go to Eleni.
Please, yeah. Eleni, can you hear us? Eleni from the Technical University of Crete in Greece. Are you online? Okay, we'll go to the next one. Zohair Bona from Cyprus Institute. Zohair, can you hear us?
Apologies, Rami. Eleni is now in presenter mode, so she should be able to hear us, hopefully.
Okay, how do I get out of this? Okay, maybe I should stop. Okay.
I think you could just stop your camera if you like, and Eleni, can you hear us?
Yes, can you hear me also?
Yes, we can hear you.
Let me see, how can I share my screen? Because I had an issue on the previous day.
It should be on the top where it says sharing, show screen. Now you're in presenter mode, you should be able to. If not, I can...
Can you see it maybe?
Yeah,
I mean, it says that
yeah. No, now you're in presenter mode. You should be able to see the share screen on the top right.
yes, I see it, but it doesn't let. Give me 1 second. Allah. I think now you just see me, but you don't see the share screen.
Okay. We can definitely see you, but you should be able to, where it says show screen. Maybe wait, stop show screen. No. So it should be on the top right where it says show screen.
Yeah.
If you click the little arrow, it will give you all the options.
Oh, yeah, that's where I am. It just doesn't want me to. Oh, change presenter, no. I'm so sorry about that.
It should be at the very top.
Yeah. I mean, I'm seeing it. It just doesn't let me share the screen, and because I'm in Australia, I wasn't able to join the training session. Can you now see it? That's no. Okay. That is odd.
Let me see if I can. Have you already sent me your presentation, correct?
Yes, you already have that.
So if I make myself presenter, I will share your presentation. Okay.
Okay. Yeah, let's do that. Yeah.
Do that to save you time. Just a minute. Okay. Okay.
Great.
Okay, so you can start.
Oh, great.
Just can you please change in the
The display.
because we're seeing the next slide and so on.
Is that okay? Can you see it okay now?
I think we still see the okay, yeah. Perfect.
No, it's fine. Great.
Excellent.
Thank you.
Okay.
Okay. So yeah, thank you so much for that, and hello everyone. My name is Eleni Dobrou, and I'm currently a research fellow at the Technical University of Crete, and also an assistant professor at the University of Crete. And today we are going to just see a snippet of how fire events can actually affect the future of the Mediterranean region. Next slide, please. How can I change the slide? Can you please? Oh yeah, thank you. So just to get everyone on the same page, the reason why we're interested in fire events is because the past years we have actually seen an increase in severity and intensity, especially in the Mediterranean region. And this is also attributed to the type of fires and the type of combustion we have. Next slide, please. Perfect, thank you. So there are two types of combustion phases. It's the flaming and the smoldering combustion. During the flaming combustion, we actually have flames and that they're visible, whereas during the smoldering combustion, this is the residual burning, which actually happens either after a fire has been completed, so the energetic part has completed, or we can actually have smoldering fire events by themselves. The main difference in their composition comes to the fact that flaming has more oxygenated compounds, whereas smoldering has secondary production of species such as organic aerosols. Next slide, please. And I will talk as the slide changes. So there are two dominant regimes that we can have in the plumes that are generated by the fire events. We can have the oxidation-driven condensation and the dilution-driven evaporation. During the first one, we have the emission of volatile and semi-volatile organic compounds that can get oxidized, resulting in the formation of second organic aerosol. And that can lead to a net increase of organic aerosol mass. This typically happens during flaming combustion. But as the plume moves downwind or we can have more mixing, then we move and transition towards the dilution-driven evaporation. And in this case, due to the mixing of the background air, we have loss of primary organic aerosol and therefore a net decrease of organic aerosol mass. And this is typical from smoldering combustion. However, these two chemical regimes can actually interchange between the two combustion regimes. And a way to actually distinct those is by using light-absorbing carbonaceous species. Next slide, please. And we have actually used these species in a combination of main gaseous and particulate species. So let's first take a look on how we can actually differentiate the combustion phase and the organic dominant chemical regimes. Next slide, please. And I'm going to first take you on a trip to the United States, and you'll see later on why this is connected to the Mediterranean region. We used real-time data that were sampled for 13 different fires through to the FireX AQ campaign at the Boise deployment back in 2019. And for the interest of time, I'm just going to focus on one of them. Next slide, please. I'm just going to present the case of a grassland fire, which is named William Flats. And this is similar to fires that can actually occur in Greece. In order to differentiate the combustion phase, we use the relationship of oxygenated carbon versus semi-oxygenated carbon to calculate the modified combustion efficiency. And this is a metric that we use, it has a set limit of 0.9. And above that limit, we are on a flaming combustion, and below that limit, we are on a smoldering combustion. As we can see here in this plot, we have a wide range of these specific parameters. So we are in a combination of flaming and smoldering combustion, which is a usual case for the Mediterranean region. Next slide, please. And then if we use that, the way to differentiate the chemical organic aerosol regimes is to use actually the carbon monoxide, the water-soluble organic carbon, and the ratio of these species with black carbon. And here I'm just presenting an example that we can see that we don't have a distinct correlation of these species, but we see that through the sampling of the plume, we see an increase of all the species. That means that we are moving from an oxidation-driven condensation regime to a dilution-driven evaporation regime. So now that we know all these things, next slide please, we wanted to find a way to actually incorporate these to the Mediterranean region. Next slide please. And we are going to start first for the 2023 Greek fire events, and we're going to see later on why this is connected to the future. For the Greek fire events, we use the weather research and forecasting model coupled with chemistry, known as WRF-Chem, and we use the 2x2 kilometer resolution. And here I'm just presenting the example of the July and August fire events and the percent difference. And the percent difference of the PM10. And as we can see, we have a 40 to 80% a difference in both months. And if we move to the next slide, we are going to see that we can have this difference also for the elemental carbon. And as we can see, this is also driven by the wind fields, and especially for August, we had a southern wind field. So now to combine these for the future events, if we move to the next slide, we take the case of the 2023 fire events and we use Joule's Inferno to estimate future fire emissions and burnt area. Then we use the grassland vegetation and chemical characteristics that we don't have for the future for extrapolated for the US cases, and we make a prediction for the same fire events for 2045. And as we can see for the case of PM10, we have a 100% increase. And that means that if the fires continue towards that direction, we are going to have catastrophic events in the Mediterranean region. So to conclude, if we move to the next slide, we have seen that we can actually accumulate and combine knowledge from different regions and apply them in order to do forecasting for the Mediterranean region. And with that, if we move to the next slide, I would like to thank the funders and the collaborating institutions. I would like to thank you all for your attention, and I'll be happy to take any question. And thank you very much for the help on the presentation.
Thank you, Eleni. Thank you very much. Let's see if we have any questions in the chat.
Thank you very much, Eleni. Participants can only do this via chat, or can people also ask questions? Only chat.
Just by the chat questions, yes.
Okay. So I think we can say John is here. The technical problem solved. Great. Excellent. Good to see you. Thank you, Eleni. Thank you very much for your presentation. Apologies for the lack of maybe clarity. We should maybe mention to all participants, if you have questions for any of the talks, please type them in the chat as they come along. So by the end of the talk, we have the question hopefully to address. It seems that we don't have anyone right now, and we're a little bit behind time because of technical problems. But we appreciate your contribution, Eleni. Thank you very, very much. And I think now we have our invited keynote speaker, Professor John Svier, who will have 20 minutes to tell us about atmospheric supersite in the Middle East, challenges and opportunities. The floor is yours, John, and good to see you.
Hello, can you hear me?
Yes, we can hear you well. We can see your slides.
All right. So first, my sincere apologies for some technical problems, and I'm very happy to join this workshop. My talk is on, sorry, I have to minimize the slides, to minimize the small thing, which is, right, okay. So my talk will be on atmospheric supersite in the Middle East, and I would like to show you here a bit of challenges and opportunities for our community here in the region to establish such supersite. The pictures here are pictures from the supersite that are in Cyprus. So my presentation will be first dealing with why do we need supersites in the Middle East? What should we measure in these supersites, where we should consider to establish them, how they currently look like for the few of them which already exist, from where we shall start as well, and recommendation. So first, why we should establish such supersite in the region? First, because the region, as you know, is located at the interface of two largest deserts in the world, the Saharan Desert and the Arabic Desert, so with a lot of dust. We have also a lot of fossil fuel combustion. This is a satellite picture of tropomy of color-integrated NO2, and that shows that the Middle East, like Europe, has a very strong, intense hotspots of combustion of fossil fuel. But our place also, because it's very sunny, has a lot of secondary pollution with ozone. And in terms of the combustion of fossil fuel, the region here is on a rising trend for CO2 emissions, for instance, by comparison with Europe, which is in a decreasing trend. So we are in a region which has already high levels of pollution from different types of sources. But also because we have missing some critical information about how this pollution affects the health. And this is a picture showing how the size of particles can enter very deep in the lungs of human. And basically, big particles will remain at the throat level. PM2.5 will enter in the lungs. Ultrafine particle like black carbon will go very far in our bodies, and somehow this information shows that the smaller particles are the biggest health impact they have. And currently we are missing this type of information to assess the health impact of particles. We are measuring PM2.5, PM10, but we are not measuring ultrafine particles. We are not measuring black carbon in air quality networks. And this is typically why we should have supersites, to better document this type of small particles. Also, because in the region, I mean, there is not a lot of observation. This is the map of global stations operated by the World Meteorological Organization. If you see here, there is nothing in the region. There is no regional, there is no global stations measuring atmospheric composition, and this is a clear gap on the map. Who will be the first to establish it in the region? That's
I think we have some technical maybe glitch with John. He's paused again. Hopefully we'll give him a second or two. I hope we get him back online. Sharbel, you can hear me? Can you hear me?
Yes, I can hear you clearly. Yes,
So I think
exactly. Something
frozen.
happened. Yeah.
I thought initially it was intended because he paused at an exciting moment to say who was the first to establish a global supersite in the Middle East. But it then turned out not to be intentional, but it was very dramatic. Okay, now we have only the slide, but no John. John, you're muted. Can you please unmute? We have you back now, but you're muted. Thank you.
okay.
John, and we didn't hear you from the time you asked the question regarding who will be the first to establish the first site.
Okay.
We stopped there. So site 5.
Can you hear me now?
We can now hear you and see the slides, but if you could go back, please, to slide 5, I think that's where you stopped.
This one.
You paused at the time we were asking who would be the first to set up one, and then we lost you.
Okay, I'm sorry for that. So thank you for alerting me. I had a loss of internet. So yeah, I was mentioning that the region here has a strong levels of pollution, but currently critically missing global observation stations. This is a map of global GAW stations operated by the World Meteorological Organizations. And there is no such observation, not such global stations in the region here. And the question will be, who will be the team establishing these first observations, which currently are critically missing. My comments, my next step is what should be measured within the atmospheric supersite. And the new EU Air Quality Directive, which has been set up a few months ago, recommend detailed measurements of fine particulate matter, PM2.5, within these supersites, and recommend to perform detailed chemical analysis of PM for the further source apportionment. So atmospheric supersites have the clear mandate to perform such observations using offline and online techniques. These are online instrumentation that can provide you a very detailed chemical analysis of PM. And this type of information allows you to go back to many different types of sources are shown here on the picture and be in capacity, if it's real-time observations, to explain what are the main sources contributing to PM pollution episodes. This can be done atmospheric supersite in PM2.5, can be done in PM10, but why not also in PM0.1 for ultrafine particles, which is a green concern. The new Air Quality Directive also recommends the measurement of ultrafine particles, black carbon, as well as oxidative potential. And so there is a clear need for the supersite to perform this type of observations. However, it's not just trivial to measure these species. I give here the example of black carbon, but the same could be for the others. Black carbon is estimated as a microgram per cubic meter and is derived by instruments such as the ethalometer, which is shown here. But then you have to correct it with the mass absorption cross-section. And this coefficient can range by a factor of 2. If you don't constrain this MAC value, then your black carbon may be off by 100%. So how to obtain this type of proper measurements is to perform EC, elemental carbon analysis, and that's why the European Commission recommends to perform co-located BC and EC measurements, so that we have a mean to constrain one against the other. And this is the way you can to derive this MAC value, is basically to perform filter-based measurements, get EC and OC measurements, and correlate it with BC. So it's just an example of measurements that should be considered in atmospheric supersite, but not just trivial and just not need only require the plug-in of an instrument, but much more behind. Another part of the directive which should be considered for atmospheric supersite is the natural contributions such as desert dust, and we have a lot in the region, and how we can easily subtract this natural component with sufficient certainty to PM2.5 and PM10. And this is a very growing concern because several countries in the region are putting ambitious targets to reduce PM2.5 and PM10 to improve their air quality. But then they should have a mean to better remove the natural component of desert dust in their reporting. And this is not trivial. The methodology proposed in Europe may not work across the Middle East because we are surrounded by dust. But there are some new approaches that should be considered within supersite. I give you here the example of an instrument that can provide real-time measurements of dust in PM10. You will see more on this presentation later this afternoon by Eleni Kolinziki on the aerotape instrument. But this type of measurements really help to better apportion the fraction of dust. And I give you here the example of a high time resolution source apportionment we have performed in Cairo for the dust, showing that 60% of the dust in Cairo is not either from traffic or desert dust, but comes from the city itself, and it's a natural component driven by wind speed. So in this case, and for Cairo, this careful source apportionment of dust has been performed thanks to high time resolution measurements of PM, and in this case, we could, with a good confidence level, conclude that 90% of the dust is natural origin. But this, of course, must be considered in other places, and atmospheric supersite here again are a good place for conducting this type of assessment. Another question raised is where this supersite should be placed in the Middle East. Again, the new air quality directive in Europe is telling that this supersite should be both at rural background and urban background. And this is very important. This should gather also long-term observations. So if we really want to be quite inclusive and provide comprehensive assessment of air pollution in the Middle East, atmospheric supersite should not be just in urban environment supporting air quality networks, but also in rural background. And I will give you here the reason why. This is a picture which shows the percentage of the pollution for many European cities and the contribution of their own pollution. So basically 0 to 20% means that the city will contribute to 0 to 20% of the pollution of PM2.5 they record within the city. So basically you can see here from this picture that from 70 to 80% of the PM2.5 pollution in European cities come from regional background, meaning that it's not produced by the city itself. So there is a clear need in Europe, but the same stands for the Middle East, to perform and better characterize this regional background pollution. Sources in the Middle East are numerous. I will give you here a few satellite measurements, observations. This is from TROPOMI, and this is SO2 measurements conducted over a year period in the region, which shows that there are some hotspots in the region where we should consider to put supersite that will be better to in capacity to better understand the importance of these sources and their trends over the year if we want to mitigate them. Another picture is not SO2 co-integrated but NO2. So SO2 relates mostly to the oil and gas, NO2 to the combustion of fossil fuel. It's an interesting parameter because somehow NO2 is collected also with ultrafine particles, with black carbon, for instance. And you see that you have a lot of hotspots in the region which are connected to the big cities. So all the time you have a big city, somehow you have a hotspot of NO2, which is related to the combustion of fossil fuel and quite often to traffic emissions. So this is another reason where you should consider to put your supersite, is to better document also these hotspots, send them, see over the time the trends. Another map is the methane supersite emitter from the oil and gas. Here again, some regions are strong emitters of methane over the region, and this needs to be properly monitored because reducing methane emissions, of course, will mitigate the impact of human activities on the radiative forcing. And showing here recent measurements, we have compared of CO2 and methane performed in the UAE and in Cyprus, showing that the signal in the UAE is much stronger than the signal in Eastern Med, which is somehow consistent with the fact that these measurements in the UAE are downwind of major methane emitters of the Middle East. Another source, of course, is the dust. And this is a recent paper showing the main hotspots of dust in the region. So here again, there are several hotspots in the region, and supersite should be carefully located to document the impact of these sources and their trends over years. So while presenting you briefly why we need supersites, what they measure and where they should be located, I wanted to give you here a few examples of how a supersite look like. And I took, of course, first the example of what we are doing here in Cyprus. So we have established a network of atmospheric supersites with different background. We have regional background, urban background, free troposphere, and marine environment. We are performing a lot of different measurements: air quality, aerosols, clouds, reactive gases, greenhouse gases. And also very importantly, we are connecting this Cyprus Atmospheric Observatory to a large number of networks in Europe and in the world. Why? Because we need to get supported by this network for standard operating procedures, for calibrations, for data centers, for trainings. So operating atmospheric supersite also does imply being part of these networks and benefit from their structure. And these observations in Cyprus provide a very wide range of observations from supermicron aerosols, submicron aerosol properties, greenhouse gases, radiative flux, remote sensing, wet dry deposition, reactive gases as well. And also very importantly, they are reported in real time and open access so that you can always have access to this data and you know what are the different types of pollutions which impact the island 24/7. The supersites will be also supported not just by online instruments put within stations, but also by a strong offline infrastructure. And we have here a laboratory we have established, the Cyprus Institute, which perform offline analysis of aerosols, what I mentioned just before for the source apportionment. So we have a set of instrumentation and a full range of accreditation to perform high quality observations. So this is another component that should be considered when you establish a supersite. It's not everything about measuring within stations, but also having the capacity in your labs to better document the different types of pollutants and their sources. One of my last point is from where shall we start? So again, here I don't have a magic recipe to tell you how to establish a supersite, but I will give you just one example that you may consider as a good one. So we have recently established a very good collaboration between the Cyprus Institute and Khalifa University in Abu Dhabi, in the UAE, to establish two supersites, one in the desert at a regional background place and one in Abu Dhabi for urban background. So how we have developed this collaboration, and this is a picture of their laboratory and their expertise, which is strongly related to remote sensing, starting by signing an MOU with us, and starting with the PhD co-supervision between our two institutions, starting installation of greenhouse gases that was last month. This month was to develop and install real-time dust monitoring, and next January to further develop the stations with more instrumentation in situ. So this is one example. I'm sure there are many others. I'm sure Rami, who is chairing this session, can give a very good one for Qatar because he's leading the development of similar supersite in Qatar. But I think this is a good time frame now to start to discuss how interconnecting these different types of supersite to make a consistent network. My conclusion and recommendation for my presentation, I wish I have convinced you that there is an urgent need to develop such a dense network of supersite in the region. First, to fill in current observational gaps, but also to better document the regional pollution. We need to better constrain here the concentrations of pollution, the chemical composition, their emissions, their sources, and also their long-term trends. These supersites should be equipped with a large range of state-of-the-art scientific instrumentation, in priority with aerosols, which are responsible for the stronger health impact of air pollution, and with this in priority to better understand the chemical composition of PM, including dust, but also emerging pollutants like ultrafine particles or black carbon. Supersites should be established both in urban and rural background sites. This is very important when you want to better distinguish the local city-based emissions from the regional background. This is very important for local stakeholders. Efforts should be made to integrate international networks because they do exist and they are well established, and you can benefit from their operational structure. They can help you with the proper setting of your SOPs. They can train you. They can help you to calibrate your observations. They can help you to provide a framework to disseminate your data and give them an open access. Last but not least, the construction of supersites, I believe, it's difficult to make it alone. It requires very strong international collaboration with scientists having the knowledge, the capacity to enhance your observations, and to help you to perform long-term measurements. And with this, I would like to thank for your attention.
Thank you very, very much, John, for persevering and for getting through all the hurdles to present this excellent talk. It's fantastic to see the new efforts in the Middle East with the super sites, and I look forward to seeing more of this and hopefully more sites being developed. I'll just quickly check if we have any questions online. Eleni, you can tell me, please, if we have any questions. Do you think any? I don't see anything in the slides, but John, you mentioned something about Cairo quickly, that 90% of the mass there was natural because of city dust and regional dust. Did I hear you right? You said this can be removed. Is this, you made this comment, or did I just imagine it?
That's a very good point. I was sure somehow I was expecting a question from you about that. I know that, for instance, in some countries like the UAE, they have put very ambitious targets for reducing PM2.5 and PM10. And it may be very difficult for them to achieve this objective. And in Europe, we have already implemented a way to remove the natural component of dust. And I showed you here in my slide that you have to do it with a good level of confidence. So not all types of dust is natural. I mean, the road dust, it may be from desert dust, but if you had no cars, there will be no road dust. So in this case, you cannot claim that this type of dust is natural. So you have to better understand and provide scientific evidence that some of your dust is natural, some of them is not. So this source apportionment of dust is very complicated because dust is somehow the chemical composition of dust is mostly the same everywhere, and the same typical aluminium, titanium, etc. So it's quite difficult. But what we have seen in Cairo is that, and we have seen it also in Cyprus and in other places, is that there is what we call city dust that is driven by wind. And wind is natural. I mean, whatever you do, wind, you cannot stop. It's a natural component. So wind-blown dust is something that we can still discuss what is if this dust is natural or not, but wind is natural. So if you have wind-blown dust over the city and it's important, like 60% in Cairo, which has some dust and some wind, then you may be able to remove it if you provide strong scientific evidence. And I believe the scientists can really support networks here with such observations, such networks, such super sites, and provide open access information as well, so that it gives a strong support to the air quality operators to remove this natural component. I think it's a very hot topic in the region, and I think we need to end up all together with a method that is interoperable. What is working in Cairo should work in Doha, should work in Abu Dhabi, should work everywhere. We should define our own methods in the Middle East to remove the dust, because the method that is developed in Europe is not working for us.
I agree 100%, and I think this is a very important topic that I think is very relevant to most of our cities here, given the nature of surrounding areas by cities with natural dust. I just want to add one comment before we move on because of time. We have the ability to do this, and we can collectively come up with a method to account for it, but this will only remove it for compliance purposes. So for environmental compliance and for meeting the regulations and exceedances, you can. But what does it mean for health is a completely different question, because we cannot remove it for health. We're still breathing it. And I think that's a very, very fundamental difference between environmental compliance and environmental health, and we need to keep this in mind.
That's exactly, Rami. We should not consider that because it's natural, we should not have an impact on health. That we have to be very careful in the message we deliver to our stakeholders. And that's why we need to deliver it, as a community, not that as one group, but all of us together to have a more impact.
Wonderful. Thank you, John. I think we can talk about this for another 2 hours, but we'll move on because of time constraints. We have a very tight schedule. So I think Kenneth, I believe Kenneth is available. He had some technical problems, but I believe he's available to speak. So if so, Kenneth from the Cyprus Institute, Kenneth Sean, he will tell us about UAV observations to reveal new insights into dust particle morphology and orientation. The floor is yours, Kenneth. You have 10 minutes. You're muted, Eleni.
Thank you, Rami. Kenneth is here with me, so he will present now.
So, hello everyone. Can you just confirm that you can hear me?
We can hear you well. We can see your slide. If you just make it in full screen, that would be great. Thank you.
Yes, that's my plan. Just let me move this panel away. Do you see the screen in the right mode?
If you could just switch the display, please, from the setting, and then it will be good. Now, excellent. You can start. Thank you very much.
Excellent. Thank you. Yeah, thank you so much for having me here today. I apologize for the technical issues. So today's talk will be about dust particle morphology and orientation, and this is a joint PhD project of the Technical University of Darmstadt and the Cyprus Institute. So basically, just to give you a very brief idea about dust particle shape. So I guess most of you know that dust is not spherical. So on the left-hand side, you can see some sample dust particles. And with the arrows, I tried to match this to some modeled shapes. However, this is really sparsely investigated, and this is adding a lot of complexity. I will explain on the next slide. And the orientation, just to make you aware of what that means. So basically, most of the papers assume that dust is randomly oriented, like shown on the left side of the image. But however, there are some studies saying under certain conditions, dust may be aligned, like oriented, and in this case, vertically. And of course, this has some impacts on remote sensing retrievals and atmospheric models. So this is why we care. For morphology, it is again sparsely investigated, and there are studies showing that the non-sphericity of the particles increase the mass extinction by about 40%, and it of course has a strong influence on processes like sedimentation. And the orientation is important for AOD modeling, etc. And it was shown, for example, in 2007, so some time ago, that the orientation caused a 10% decrease of AOD, and this was related to the electric field. So what do we do, or what did we do actually? Because we need data, so we had a campaign this year in April and May in Cyprus. And basically, we evaluated new instrumentation techniques like Cobalt and GPAC. I will explain what that is now to approach these questions. So to keep you aware of the most important dust event we had in this campaign, I'm briefly showing this slide indicating a very intensive dust event on the 17th and 18th of May this year. Which was predicted well by the CAMS model in this case, and we could see this pretty well on the LiDAR as well, that the plume was coming down to the boundary layer late evening on the 15th of May. And you can see it was a pretty strong event, and we were lucky to fly with our instruments then. So regarding the shape and the morphology, the plan is to analyze the collected particles under the microscope. And for this, of course, we need to collect them. And you can see on the left-hand side, this is an impactor system, which can be turned on under certain altitudes. And then particles will be collected on this impactor system, which is a adhesive pad. And you can see on the right-hand side, this is a slightly modified version because we were able to integrate a so-called scanning electron microscopy grid. And the advantage is that you are really way more, you're able to get a way better representation of your particle. So on the left-hand side, you can see one example. This is a particle we collected on this grid, and on the right-hand side, you can see its three-dimensional representation. And obviously, the most interesting thing is the height, because this is tricky to get due to the constraints of the electron microscope. However, this grid really improves a lot, and we were able to reconstruct this by turning and tilting the stage of the microscope. So this is one first result. The orientation was approached by a so-called compact optical backscatter aerosol detector, Cobalt, and the main idea is the following. So on the left-hand side, you can see the UFV with two instruments, one looking into horizontal and one into vertical directions on two wavelengths. And while flying, the basic idea is that if the particles are oriented, the cross-section must differ. This is the main idea. You see, so you would have a different cross-section in case the particles were vertically aligned. So I tried to explain briefly what we did. So before each flight, we did a ground calibration to basically calibrate the two orientation channels relative to each other for both wavelengths to get like a correction factor. And for the flight data, we used the pressure and temperature to derive the molecular number density. And for both pre-flight and flight data, we used the monitor signal to normalize the data with a rolling mean to be sure we smooth out eventual problems of the instrument. So this monitor signal is basically detecting the emitted light per channel. And then we calculated the backscatter ratio. So basically the measured signal divided by the molecular signal, which was the number density and the correction factor. So this would indicate the presence of aerosols. We also derived two other indices, which is the color index indicating particle size and basically the aerosol backscatter ratio, which is just nothing else than the backscatter ratio -1 to just see the aerosol part. And then finally, look what we did. We were able to fly during this dust event I have shown on the 17th of May. And you can see this is the signal of the horizontal and the vertical instrument, blue wavelength and the red wavelength and the color index. And basically, if you take the ratio of this, you simply see the deviation between the vertical and the horizontal instrument. And this would indicate if we can assume some orientation. And the ratio of this plot looks like this. So 1 would mean no orientation, no deviation from the both channels, but we can see clearly that there is a deviation and the vertical red was weaker. However, the blue was stronger, and this is actually really interesting. And at the moment, we are trying to understand what we are seeing. And you may wonder or want to know, okay, please explain, but I must admit, this is current work and I don't know for sure, but I hope I will be able to tell you more in the next months. But it's a nice indication. And with this, I would like to thank you for your attention.
Thank you very much, Kenneth, for your very clear presentation. We have time maybe for one question, if anyone is. I'm looking at the chat just to see if we have a question. I see one from Zohair. That was for the previous talk, which, okay, that was very similar to the discussion we had. So Zohair, I hope we had that question already discussed. And I'm sorry for missing it at time. Kenneth, I don't have any questions on this, but you can comment on operational kind of challenges for this, if depending on the size of the dust event, you have limitations for where you can deploy or not deploy this kind of technology?
Yes, of course. I think, well, one challenge is that we, of course, can only fly during the night or let's say after sunset, because otherwise it would just oversaturate your signal. This is for sure one problem. And then, of course, you are always dependent on atmospheric conditions like wind speed, etc. So this is tricky. And also, we always want to fly with all the instruments, like also OPCs, because at the moment I'm calculating the expected scattering based on the size distribution. So that means ideally you need to fly your whole setup in the event.
Thank you. Thank you very much. All the best with the rest of your research on this. Thank you. I think we now move on to the next speaker, and there will be Zohair Bona from the Cyprus Institute. I hope Zohair is ready to present. And yes, I can see him online now. So Zohair will be speaking about dust over Cyprus, EarthCare, ground-based LiDAR, and UAV observations for vertical dust profiling. Zohair, you will have 10 minutes, and the floor is yours.
Okay, 1 second.
Yeah, we can hear you now, and you should be able to share your screen now as well.
Okay. Can you see my screen or not?
Yes, but just make it change the display settings. Go make it into full screen again, and then go excellent. Yeah, you go there and you swap the.
Okay.
Excellent.
Okay.
To go.
Okay. Okay. I will be talking today about dust over Cyprus using EMME-CARE ground-based LiDAR and UAV observation for vertical dust profiling. This is part of my PhD in Dust DN in the Cyprus Institute with collaboration from NOAA, Institute for Astronomy, Astrophysics, Space Application and Remote Sensing, National Observatory of Athens. First, I will talk about EMME-CARE satellite. It was launched in May 2024. It is too far is the biggest and most complex Earth explorer. It have 4 instrumentations: atmospheric LiDAR, which provide vertical profile of aerosols and cloud and operate at wavelengths of 355 nanometer and has a high spectral resolution receiver and depolarization channel, and the cloud profiling radar, the broadband radiometer, and multispectral imager, with the goal of studying aerosol, cloud, and Earth's radiative budget. Then in the Cyprus, we have the Cyprus Atmospheric Observatory. I am focusing on remote sensing. As it was mentioned before, Cyprus is a hotspot for aerosols, as we have aerosols from different regions, north of Africa, Asia, and Turkey, Greece. I will be focusing on our LiDAR system, which is a dual wavelength polarization LiDAR. Specifically the 532 nanometer with the polarization channel. Here I present in the 8th of April this year, we have an EMME-CARE overpass over Cyprus. As we see in the top right hand side on the map, the closest profile was around 43 kilometers away from Nicosia. And we did a back trajectory, and in some confidence we believe the air masses were coming from North Africa. So as we see in the target classification from EMME-CARE for this day, we have dust over Cyprus, mostly dust. Then we did a comparison between particle backscatter, particle extension, and particle depolarization ratio from our LiDAR and from EMME-CARE. I wanted to note that we see different wavelengths. The only conversion was done for particle depolarization, which is in red. The one is red is converted from our LiDAR wavelengths to EMME-CARE. And we see we have a reasonable agreement. Of course, the dust layer is different between our LiDAR and EMME-CARE, and we believe this is due to different in locations, as they are not seeing the same thing. But we are interested in dust. So to see only dust, we use a polyphony method, which we have one-step polyphony or two-step polyphony, which basically can be used to separate dust and non-dust. We use as an input particle backscatter coefficient, particle depolarization ratio, and I want to mention also that this is based on assumptions. So we need to assume particle depolarization for dust, for non-dust. For the case of the two-step polyphony, we need to assume particle depolarization for coarse, fine, non-dust, and mixture of fine and non-dust. So the one-step polyphony will give us total dust and non-dust. The two-step polyphony can give us coarse dust, fine dust, or and non-dust. As we see here, we applied this method to our case on 8th of April this year. And for the one step, we see that we have a good agreement about, or a reasonable agreement for the dust particle backscatter, but for the non-dust, EMME-CARE show more non-dust. And the same for the polyphone 2 step, we see coarse and fine and non-dust, and we see a reasonable agreement in the coarse and fine, but EMME-CARE again show more non-dust particles. Next, we because this method is based on assumptions, and as we see, because of for this case, for example, when we have different wavelengths, it will be sensitive to different sizes. So we will re-evaluate and validate the assumptions used to retrieve the dust component, and then we will extend our analysis to more case studies and drive the dust mass concentration separately from EMME-CARE and LiDAR datasets. And as mentioned before by my colleague, we have UAVs observation. So we will use those from past campaigns and from future one to study what is the differences and why, what is the uncertainties that we can improve or how to improve the uncertainties. And we will hope to extend the validation to different LiDAR datasets from EarlyNet. Thank you.
Thank you very much, Zohair, for your very clear presentation. And it's exciting to see this new satellite and new data products coming along. Seems like quite comprehensive. Any questions? I'm looking. I don't see any questions in the chat. Again, I'd like to encourage all participants to use the time of the presentation to write their questions during the presentation so we can see them at the time of questions. But currently, I don't see any. So Zohair, what is the information about these products in terms of the resolution, the time resolution, the spatial resolution of this kind of these products for dust?
For our LiDAR, at the time of the overpass, I used like 90-minute time integration, and EMME-CARE, I was using the raw resolution. The raw resolution is basically 100 kilometer average, because it was proven by the community that for this purposes, it is better to use the low or medium resolution because the high resolution will be too noisy.
Okay, thank you very much. Okay, Zohair, thank you for that, and we'll move on to the next talk. I think we're about 10 minutes behind schedule because of the early technical glitches we had. So we will carry on for now. Next is Aristotelis Likakos. I hope he is online, Aristotelis, and available to start. And he's from the Cyprus Institute. Can you hear me, Aristo?
Hello, now I'm unmuted. Good morning. I can hear you. Can you hear me?
Excellent. I can hear you very well. If you could please share your screen. And you have 10 minutes, please. Tell us about extending heat wave metrics to investigate warm spells across all seasons in the Eastern Mediterranean, Middle East. The floor is yours.
Can you see my screen? Am I sharing correctly?
I can see your screen very well and everything is good. You can start. Thank you.
Okay. Excuse me for the webcam is open, but I don't know why it's not showing. Anyhow, let's start. Okay, I am Aristotelis. I am a PhD student in the Cyprus Institute and National Kapodistrian University of Athens. And today I want to showcase a presentation for some heatwave metrics and how these can be extended and transformed to warm spell metrics. And along the way, I will be conducting an investigation of the seasonal cycle of warm spells over the EMME region. Now we study heatwaves and warm spells. Heatwaves specifically due to their significant health impacts, increasing the likelihood of wildfires, Along with warm spells, they have huge impacts on ecosystems and agriculture. Think of forced spring effects, think of crop failure. And we study them to build better forecasting systems and adjust policies and policy making. Now, there are multiple definitions you can find of what a heat wave and a warm spell is. All of them share three common fundamental characteristics: intensity, duration, and frequency. And climatologists use a large plethora of different climatic metrics and indices to capture these characteristics. But because heat waves are on the spotlight, they are not adjusted properly for warm spells. Thankfully, heat waves are a subset of these larger atmospheric phenomena, which is warm spells, and they can easily be adjusted, including seasonality as well. And this is the premise of today's presentation. Now, to capture warm spells, the data requirements are a daily maximum temperature at 2 meters for a reference period of 30 years. And the data that we used in this presentation come from ERA5 reanalysis from Copernicus. Now, the detection method we used is we need to have 3 or more consecutive days above the 90th percentile threshold, which is a threshold calculated from a 31-day moving window on a 30-year reference period. Now, repeating this process for every, it's the presentation. You can still see the presentation? Okay. Repeating this process across every location, it could be a grid point or a station, we can find our metrics. Now, speaking of metrics, the first one is heat wave frequency. It is defined as the number of days that contribute to heat waves from May to September, and it is easily transformed to warm spell frequency, the number of days that contribute to warm spells in different traditional seasons. And by doing this, for every grid point inside our domain, and for every season, we can perform a domain averaging. And this way, we can showcase these 4 time series, one for every season, with green is spring, red is summer, orange is autumn, and blue is winter. Now, over the past 3 decades, we also performed a trend analysis using sense slope and the monotonicity test using Mann-Kerndel's test for monotonicity. What we see is that all of the seasons have comparable ranges of warm spell frequencies. They kind of overlap with each other. But of course, there are some exceptions here and there. And this is clearly visible by taking the 5-year centered smoothing and averaging and seeing that summer is diverging from the other 3 seasons. This is also apparent by looking at the trends over the past 3 decades. We can see positive trends for all 4 seasons with statistically significant monotonicity signals. But the highest trend was found for summer with 3.4 days per decade. That means that over the past 30 years, this region has added 10 extra days of heatwave days in comparison to 30 years ago. Now, next is a metric for duration, heatwave duration. It is the length of the longest heatwave from May to September, and it is transformed to warm spell duration, the length of the longest warm spell in different traditional seasons. Again, what we see is that all of the seasons share similar ranges, and we find positive trends over the past 3 decades across every season. Again, the highest trend was found for summer, and this is to be expected because frequency and duration are 2 metrics that share similar definitions. Now, next metric is a metric that captures the intensity of these events. It is heatwave amplitude. This is the peak daily value in the hottest heatwave, and it is transformed to warm spell amplitude, the peak daily value in the hottest warm spell in different traditional seasons. Now, what we find is that all of the seasons are pretty distinct from each other, which is to be expected. The hottest is the summer, then the 2 transitional seasons, and then winter. Again, we find positive monotonicity signals and trend signals. But at this point, I want to suggest a different metric that should be looked at and evaluated. It could be a metric that doesn't look at the absolute temperatures. And to give you an example, if we were looking at the transitional seasons and we were just keeping the absolute temperatures, we would tend to keep the absolute temperatures the highest closest to the warm season, closest to the summer. What I suggest is that for this type of analysis, for warm spell analysis, we should be looking at anomalies from the 90th percentile. And this is exactly what we did with a new metric. It is warm spell amplitude anomaly. It is the peak daily anomaly value from the 90th percentile out of all the warm spells in different seasons. And by doing that, we see something very significant. Again, all of the seasons have similar ranges, very close to each other, but it is very clear that winter and spring seem to have at around half a degree higher anomalies than the other two seasons. Also, they seem to be a lot more variable than the other two seasons. Also, looking at the trend signals, the monotonicity p-values were significantly improved from the ones from before. Again, we find positive trend signals across every season, with the highest being summer and winter of around 0.3. And this means that over the past 30 years, we have at about 1 degree hotter intensity heat wave and warm spell events for these seasons. And the lowest signal for the intensity was found for autumn. Now, this was everything for this presentation, and thank you very much for your time.
Thank you very much, Mr. Tovitz. Thank you for your presentation. And I'm just looking to see any questions again. No, I don't see any questions here. Okay. This analysis you showed in terms of spatial regional variability, is this something aspect you're looking to investigate more, or you focus on the aspects you showed so far?
Yes, this is a very good question. As you've seen and you understood, we performed the domain averaging across a very wide region, the EMME region. And by taking different sub-regions inside this region, we can definitely notice, and we will notice different things and different characteristics. So the next step is by taking different domains and performing a similar analysis like this. But the first part is to simply produce this type of results for a large domain and go on from there, see what are your clues are. So yes, this is the next plan.
Wonderful. Good luck with that, and we look forward to seeing the outcomes. Thank you very much. And we'll move now to the next speaker. And our next speaker is Andreas Karbasitis. I hope I pronounced your name correctly. And you have 10 minutes, please, Andreas. You will be talking about precipitation projections in the region. Thank you.
Okay. Can you see my screen now?
Yes, all good, very clear. Yeah, please go ahead.
Okay. My name is Andreas Karbasitis, and the title of my study is Precipitation Projections and Variability in the Eastern Mediterranean, Middle East, and North Africa region based on the CMEP6 ensemble. Some introductory stuff. The Eastern Mediterranean, Middle East, and North Africa region is characterized by a hot and arid climate and very scarce water availability due to the very low rainfall amount that falls in this region. It is considered as a climate change hotspot because the temperature is increasing faster than the global average, as we see on the top right figure, but also faster than most other regions of the planet, as we see on the bottom right figure. This environmental hotspot is projected to experience significant impacts from future climate change due to both changes in the temperature, but more specifically and more importantly, due to changes in the precipitation patterns. But future rainfall projections for this region remain quite uncertain, especially the changes in the variability and the extremes, and this was the motivation for this study. Now onto the methodology used. We used a multi-model sample of CMEP6 models to analyze for this region. Specifically, we used 16 bias-corrected CMEP6 models that were interpolated at a quarter of a degree. On the table on the right, we see the names of the models used in the study. We focused on two socioeconomic scenarios, the SSP2, which is the middle of the road scenario, and the SSP5, which is the more extreme or the business as usual scenario. And these scenarios were compared to the historical reference period. For the future projections, we used the second half of the 21st century, but basically between 2051 and 2100, while for the historical period, the second half of the 20th century, between 1951 and 2000. We studied changes in both the total precipitation, the coefficient of variability of precipitation, as well as in the extremes. Also, some definitions that would be useful for later. The coefficient of variability is the interrandom variability over the mean annual precipitation. The RX1 day to annual precipitation is the percentage of the annual precipitation that falls in the wettest day of the year, basically the year with the highest rainfall. And similarly, the RX5 day to annual precipitation is a percentage for the wettest 5-day period of the year. Now on to the results. We start with the annual precipitation. Generally, I will show on the left the SSP2 scenario and the right SSP5 scenario, the changes. On the middle of the row scenario, on the SSP, we see that there will be a decrease of precipitation along the Mediterranean coast of North Africa and Middle East that reaches up to 30% locally, but in most regions will be around 10%. But also we see an increase of precipitation in the Arabian Peninsula, especially in the southern parts of it, that reaches up to 40 to 50%. In the more extreme scenario, we see that the decrease of precipitation reaches up to 30% over eastern Libya and up to 20% over the rest of the North Africa and the eastern Mediterranean, while the increase of the precipitation in the southern parts of the Arabian Peninsula is projected to exceed 80%. Now, for the coefficient of variability, on the left, we see that the coefficient of variability will increase by around 50% for most of the North Africa, eastern Mediterranean, and the Middle East. But for the Arabian Peninsula, we see no significant change in this variable. In the more extreme scenario, we see a similar pattern as in the SSP2 scenario, but generally slightly larger values. For instance, in the northern part of the Middle East, the eastern Mediterranean, we see up to 25% increase in the coefficient of variability. Now we go to the extremes. We start with the RX1 day to annual precipitation. This percentage is expected to increase about 20% along the eastern Mediterranean, North Africa, and parts of the northern part of the Middle East, while we see a decrease of up to 20% in the southern parts of the Arabian Peninsula and no significant change in the central parts of the Arabian Peninsula. In the more extreme scenario on the right, in the SSP5, we see increases of up to 30% for the eastern Mediterranean, North Africa, and the Syrian desert, but no significant changes again in the central part of the Arabian Peninsula, while a decrease of up to 20% is projected for the southern parts of this peninsula. Now to the 5 days wettest period of the year. In the middle of the row scenario, we see that this percentage will increase between 5 and 10% along the eastern Mediterranean, North Africa, and the Syrian desert, while no significant change is projected for the central part of the Arabian Peninsula, as we saw again with the RX1 day, but also we see a small decrease of up to 10% in the southern parts of the peninsula. In the more extreme scenario, in the SSP5, we see that the increases for this percentage will be between 20 and 30% in the Syrian desert and the eastern Mediterranean region, while in the North Africa will be more confined to 10 and 20%. While at the same time, in the southern part of the Arabian Peninsula, again, we see a small decrease of up to 20%. In conclusion, annual precipitation will decrease along the Mediterranean coast of North Africa in both scenarios by up to 20% and up to 30% along the eastern Libya in the business as usual scenario. In the eastern Mediterranean, precipitation is projected to decrease up to 20% in both scenarios, while in the southern parts of the Arabian Peninsula, it is projected to increase significantly, especially in the SSP5 scenario. The coefficient of variability will increase along the eastern Mediterranean, North Africa, and northern parts of the Middle East, indicating larger year-to-year variability in the precipitation. In both scenarios, extreme precipitation events will be responsible for increasingly larger percentage of the total annual precipitation in the North Africa, eastern Mediterranean, and the northern parts of the Middle East. On the other hand, for the southern parts of the Arabian Peninsula, precipitation extremes, as we saw, will account for a smaller percentage of the annual precipitation. Generally, we can conclude from this that water scarcity will increase in the North Africa and the eastern Mediterranean region, while extremes will become increasingly prevalent. Thank you for your attention.
Thank you very much, Andreas. I now genuinely hope someone has a question. I'm looking to see.
Rami, there is one from Ricardo Fonseca.
Okay.
I don't know if you've seen it, I assigned it to you, but it says, have you looked into the drivers of the projected precipitation changes?
We haven't really looked at the drivers, but it's something we are planning to do.
Yeah, excellent. Thank you very much, Andreas. Thank you for the question as well from the audience. We're moving on to the next one. I think we have two more to go. We're about 10 minutes or so behind time. And next is Narendra Nelly from Khalifa University of Science and Technology at the UAE, and he will tell us about processes to impact changing convection regimes and UAE record April 2024 rainstorm. This was a big event. Let's see some interpretation. The floor is yours, Narendra.
Can you hear me? Hello.
Yes, we can hear you.
We can.
Hello.
Go to full screen, please, and then you can start.
Hello. Can you see my screen now?
Yes, you can see it if you just go to full screen, presentation mode, and please start. You have 10 minutes. Don't think you can hear me, right?
Yeah, I can hear you. 1 minute.
Okay. So now you can please present. Yes, start, please.
Yeah, I think now it is in full screen. Hello, everyone. Thanks to organizers for this opportunity, and thanks to all of you for joining. Myself, Narendra, from NGOs Lab, Khalifa University, Abu Dhabi. Today, I will talk about how convection regimes are changing over Southeastern Arabian Peninsula, how these changes relate to record-breaking April 2024 rainstorm in the UAE. This work is done together with my colleagues, Dr. Diana Francis and Dr. Ricardo, and our collaborators. In this presentation, I will give a high-level summary of our three recent studies. First, I will summarize the atmospheric controls of extreme convective events over Southeastern Arabian Peninsula during spring season. And second, I will move from cause to consequence by revisiting the historic April 2024 rainstorm in the UAE. Finally, I will present new results on the drivers and trends of summer-type convection over Southeastern Arabian Peninsula, focusing on how often these occur and how they might evolve in warming climate. Let's start with the springtime convective system. Here we identify mesoscale convective systems using a satellite infrared brightness temperature at 4 kilometer resolution with 30 minutes time interval from 2000 to 2020. The panel to the left shows how many hours MCS occurred over 5 stations in the UAE. We see clear maximum in March, April, and a secondary peak over Alain in July, August. And to the right, I am showing the composite error 5 anomalies for these MCS days. They show all classic ingredients. For example, panel A and B show enhanced low-level moisture and winds, and panel C shows favorable mid and upper-level circulation. So in spring, Southern Arabian Peninsula experience organized intense convection, which is linked to large-scale circulation and moisture transport. When we look at how these spring MCS are changing over time, we see three key signals. They are becoming more intense, as you can see, in terms of colder cloud tops and higher rainfall in panel C and D. They are also becoming smaller in areal extent and long-lasting in duration, as you can see in panel A and B. This intensification is consistent with a warming environment where more moisture is available and convective systems can develop more rapidly and efficiently. Now I move to April 2024 rainstorm in the UAE, which many of you are familiar. This was the most extreme rain event on record for this country. On this slide, I am showing the large-scale circulation during 15th to 17th April 2024. Each column shows a different atmospheric field and each row is a different day. I will focus mainly on the middle row, which is 16th April, the day of the peak rainfall. Panel A to C, that is first column, shows potential vorticity in color and winds in arrows. If you look at panel B for 16th April, you can see a PV streamer and a cutoff low situated unusually far south over Arabian Peninsula. This feature brings cold air aloft and strong upper level forcing, which strongly destabilizes the atmosphere and favors the deep convection over the UAE. Next, panel D to F, which is second column, shadings are 500 HPA geopotential height, and arrows are winds in metroposphere. Again, 16th April, we see a well-defined mid-level trough over this region, providing a large-scale ascent, helping to organize the convection. And third column shows surface pressure in color and near-surface wind arrows. You can see deep low pressure center over southeastern Arabian Peninsula, interacting with the Red Sea trough to the west and Arabian subtropical high to the east, shown in panel G. Okay. Together, these features act like a pump, drawing warm, moist air from Arabian Sea and Gulf of Oman towards UAE. That you can see in panels J to L, where I show column integrated water vapor in shading and IVT as arrows. Again, if you see the panel K, 16th April, we see intense moisture plume and a very strong northward IVT into the UAE, indicating an exceptional atmospheric river like moisture transport into this region. So if you put together, if you put all these panels together, the picture is very clear. An upper level PV streamer and a cutoff low, a deep surface low interacting with Red Sea trough and subtropical high, and an extreme moisture corridor from Arabian Sea. All these aligned on 16th April to produce the record-breaking rainfall over UAE. One striking consequence of this event was the desert greening that followed this event. Here I am showing the NDVA percentage over the UAE for May to October for the years 2023 and 2024 for three vegetation types in panel A, C, and E. NDVA shows no or low vegetation pixels decrease by about 20% in 3 months after the storm relative to 2023. This is shown in panel B on right side. At the same time, moderate and dense vegetation pixels increased by up to about 370 and 40% respectively. And this you can see in panels D and F. And also from the spatial map, in some areas, NDVA more than doubled between June 2023 and June 2024. You can see this in panel I. This tells us that a single very intense rain event in this hyper-arid environment can strongly recharge soil moisture and groundwater and support remarkable ecological response. Now let me now turn to summertime convection over southeastern Arabian Peninsula. Based on our recent GRL publication, here we focus on May to October, when convection is often small scale, short-lived, and strongly tied to local surface forcing. We find that convection peaks in July and August over the Al-Hajar Mountains and surroundings areas. You can see this in panel C and D. These storms are driven by intense surface heating, moisture convergence from the Arabian Gulf and Gulf of Oman, and strong sea breeze and mountain breeze circulation. So summertime convection is very much a boundary layer and mesoscale story, but it is modulated by large scale circulation as well. Yes, to see larger circulation pattern associated to these convective days, we use clustering technique to and then associated with the summertime convective events over this region. Two main patterns emerged from this clustering analysis. About 80% of the time, convection occurs when there is an anomalous ridge to the east, which helps funnel moisture and favor ascent over our region. You can see this in panel C. In the remaining 20% of the cases, convection is linked to an anomalous low to the west or south, again enhancing moisture transport and lifting. You can see this in panel D. So even in summer, convection is not purely local. It is tried to prefer large-scale configuration that modulate how much moisture is available over this region. Next, I am showing the trends of these summertime convective events. In panel A, I am showing precipitative convective days over southeastern Arabian Peninsula region during summer season. From 2000 to 2024, warm season convective days are increasing by roughly 1.4 days per year. I'm not showing here, but these events are becoming larger in areal coverage and also longer lasting. This means seasonal burden of convective rain, both in space and time, is steadily growing. Looking to the future projections, CMEP6 projections under two SSP scenarios show a statistically significant increase in the summertime convective days, roughly about 0.038 days per year. So both observation and climate projection point to more frequent and more persistent summertime convective activity over southeastern Arabian Peninsula. And to summarize, we see consistent evidence that convective regions over the southeastern Arabian Peninsula are changing. Springtime MCS are become more intense and long-lasting. The April rainstorm shows how extreme convection can rapidly transform a hyper-arid landscape. And in summer, both observation and climate position indicate more frequent, larger, and long-lived convective events in the coming decades. These findings have important implications for flash forwarding, infrastructure design, and water management in this region. If you have any questions, please contact me by email. Thank you very much for your attention.
Thank you very much, Andreas, for Narendra, for your talk and this good analysis of this big event. Any questions? Eleni, do you have any questions in the chat, please?
No,
I can't see any.
Yeah, no.
Okay. Narendra, just one very brief one. On historical kind of records, has anything like this been witnessed before in terms of the scale of this, the duration, the scale, or was a one-off?
This is the first time.
First time on that scale?
Yeah.
Okay. Thank you very much. Thank you, and all the best. Okay, we have our final presenter, George Zitis. George, if we were to stick the time, you have 1 minute presentation, but that would be unfair. So you have 10 minutes.
Thank you very much.
Coffee will just have to wait a little bit.
I'll try to be brief. Yes. Can you see my screen?
You can see your screen, and if you can go to full screen mode, that would be fantastic. And look forward to your talk
perfect.
on 2024 Hajj heat disaster, glimpse into the future.
Yes, thank you very much. So my name is George Zitis. I'm a research scientist at the Cyprus Institute, and I'm going to present an analysis of the 2024 heat event during the Hajj, and also some future temperature extreme estimations for the Mecca. This is a regional effort, largely motivated by the MENA Cordex initiative. And yes, what has motivated really this study was the very extreme temperatures that were reported in Mecca during the Hajj period last year. So there were records of nearly 52 degrees Celsius. Hajj is one of the largest religious mass gatherings in the world. And in this case, there were nearly 2 million participants that were registered. Unfortunately, there were a lot of casualties. More than 1,300 people were reported as fatalities, according to the media. And there were also several thousand people that were also impacted by the extreme heat. This type of temperatures, according to previous analysis, is what we expect to occur in the region towards the end of the 21st century. And we have seen previous studies on extreme events in the region. There are several studies that all confirm these estimations. Also, we know that particularly the MENA cortex ensemble tends to underestimate the observed temperature. So we really consider that these future estimations are quite conservative. There has been a preliminary attribution analysis by the EMME-CARE group, which is also collaborating in our study, contributing to our study. And according to this attribution analysis, it is quite certain that this event has been strengthened by climate change. So it's really attributed to anthropogenic climate change. However, similar events have occurred in the past, but this analysis is really based on reanalysis data, not on station observations, and takes into account, for example, temperature anomalies, pressure, and wind speed anomalies during this event. So our objective is to really look a bit in more detail what happened during the HATS 2024 extreme case in terms of temperature anomalies, thermal comfort, and the role of humidity. We have been raising awareness about future occurrences of such events and see if such hot weather conditions can become more frequent or more intense in the future. And we also aim to encourage further studies on the causes and predictabilities of these extremes, which actually we see them occurring earlier than what we have been projected in future assessments. Finally, we also discussed mitigation solutions for further consideration by policymakers, and this is to bridge the gap between hazard characterizations and also actionable risk reduction strategies. A few words about the data. So we have used station observations from the global summary of the day, and these are daily maximum temperatures. Then we also incorporated the ERA5 land reanalysis that provide data at hourly temporal resolution and at the spatial scale of around 10 kilometers. For the future projections, for up to the end of the century, we have used this MENA cortex ensemble, and we use daily maximum temperatures from 7 regional climate models that are at a relatively coarse resolution of 50 kilometers, but are quite skillful and optimized for the regions, since these have been developed from groups that are active in the Middle East and North Africa. To get an estimation of future uncertainty with regards to scenarios, we have used 2 RCPs, a business as usual RCP 8.5, and a more intermediate scenario, which is RCP 4.5. In order to bias adjust our projections, since I have shown that these are quite underestimating maximum temperatures, we have used the quintile delta mapping. We have used the Humidex index also for assessing thermal comfort. And finally, we did some extreme value analysis based on the generalized extreme value approach and the maximum likelihood for estimating the shape and other parameters of the distribution. And I will move to some results. We've seen from the observations that the average daily mean temperature in June is in Mecca is around 36 degrees. The average daily maximum is nearly 44 degrees Celsius. And what was observed during this period, this record high is nearly 52 degrees Celsius in something that was never recorded before. And here I show the temperatures and the maximum temperatures on the top and the temperature anomalies on the bottom based on the ERA5 land data sets. You can see here an estimation of the resolution, get a feeling of the resolution of this data set. And here we depict also locations of interest to the Hajj pilgrimage. And from this picture, we see that the ERA land dataset failed to capture these extremely high temperatures. Throughout this domain of the Arabian Peninsula, we see that the temperatures were below 50 degrees Celsius. However, what is really useful from this dataset is that we can see hourly values of temperature and humidity. And here we have calculated the humidex, a widely used index for assessing thermal comfort. And we really see that for several days during this period, the values of humidex have exceeded this great discomfort, actually every day. And for several occasions, even the extreme dangerous conditions. And here we also try to do a sensitivity analysis and calculate this humidex based on daily averages, which is what we see here with the cross symbol, and hourly values. And we see that really using daily average is not a good approach. And for this reason, it substantially underestimates the humidex values. So we really need to use sub-daily fields in order to get more representative conditions. Now let's move to the future projections. Here is the temperature, maximum temperature distribution, and we really see that the RCMs at the 50-kilometer resolutions, they substantially underestimate the observed temperature, which is the distribution that is hatched here. I need to mention that there is at least a 500-meter difference in altitude between models and the stations. We applied this quantile delta mapping that has been really effective in adjusting the bias of the models. And then we apply this methodology also to the projections, and we see the results that we see here for the two scenarios. Particularly for the business as usual pathway, we see that there is a shift towards warmer temperatures and also a change in the shape of the distribution. This indicates more extreme variability. And if we consider all summer days, which is what's shown here in the distribution, according to the business as usual pathway, there is about a 3.5% probability of exceeding this extreme case, what we observed in 2024. Particularly for the end of the 21st century. If we consider the intermediate pathway, this probability is much lower, and it's very unlikely to exceed this 52 degrees Celsius threshold. Here we also see time series of projected maximum temperatures for the two scenarios, and here we highlight the periods that we expect that the Hajj will occur in the extended summer period, which here is considered from May to September. Again, we see that following this business as usual pathway will result in very likely exceedances of this 52 degrees Celsius threshold. If we consider the intermediate pathway, we can be much more optimistic. And finally, this is the extreme value analysis. We did this to calculate the return periods of the expected return period of such extreme cases. According to the observations and the historical simulations, this type of event is expected to occur once in approximately 70 years. However, when we go to the future scenarios, here is the case for the middle of the century. Here we see quite similar results for both scenarios. We expect such occurrences every 1 to 20 years. And if we go to the end of the century, this return period is really reduced. And for the business as usual pathway, we expect such events to occur on an annual basis. On the intermediate pathway, the return period of such events is near once every 6 or 7 years. Some concluding remarks. So the maximum temperature during the Hajj period of 2024 was record-breaking. We've seen that the temperature anomalies was around 8 degrees, and this event, according to our analysis, is expected to occur once every 70 years approximately. This event, the temperature anomalies were not well captured by the state-of-the-art reanalysis, which is the ERA5 land. We have seen that the combined effect of high temperature and humidity was one of the key factors that resulted in extreme danger conditions for multiple days. Despite the fact that the MENA Codex RCM systematically underestimates maximum temperature, this was resolved by applying the quantile delta mapping bias correction approach. And we expect that, according to future projections, these events will become a regular occurrence only under the business as usual pathway, and this is the case only towards the end of the 21st century, but highlights really the need for urgent mitigation actions on a global but also on a regional basis. This analysis was supported by the EMME-CARE project and also by the FutureMed cost action, and is currently being under review as a perspective manuscript in the journal called NPJ Natural Hazards. And with this, I would like to thank you for your attention and open the floor for any questions.
Thank you very, very much, George. We have a couple, maybe minute for question. Eleni, any questions?
There is one from Zuhir. Thank you for the nice presentation. What about the winter time? Do we expect any unusual low temperatures?
Something that we didn't look in this study. However, from previous analysis, I think that in this region, also winter temperatures are expected to increase, but we didn't look into extreme low winter temperatures. Yes, this is something that we could look into the future. The work of Aristotelis is somehow trying to answer these questions, since he's looking into warm spells and extreme temperatures throughout the year. But of course, can also have a significant impact, not only on humans, but also on ecosystems.
Okay, thank you very much, George. Just a very brief remark quickly on this Hajj risk, because as you know, the Hajj follows a different calendar cycle. So it has a 10-day every year shift. So it has a very strong seasonality. It's now heading back towards moderate seasons. It's currently in June. So I think every 30 years we'll have the kind of the cycle. So it's definitely going to come back again as a risk on that time scale for sure. And this will continue
this
to be
is something, yes, this is something that we have considered in our analysis, and you can see here in the blue bars the periods where we expect the Hajj to occur during the summer season.
Okay,
but also there are other mass religious mass gatherings in the region and in other parts of the world. So really this analysis and the proposed mitigation measures could provide some insights for other cases.
Indeed, no doubt. Thank you very much once again. I'd like to thank all speakers, and apologies for the delay of the time scale because of the glitches we had in the start. I'll leave it now, hand over to the organizers to sort out the time and the coffee break and the next session. Thank you all very much, and I wish you all a great rest of the day and a productive following sessions. Thank you.
Thank you, Rami. So, Eleni?
Should we have a short 10-minute break since we had a delay? So we're back at 11:05 with our invited speaker.
Okay. So see you at 11:05. and
Yes.
we will begin with Dr. Uzu, the keynote speaker at 11:05. Thank you.
Thank you. Hi, Damien, can you hear me? Damien, can you hear me?
No, yes, I can. And I can activate the sound.
Damia?
I will make you a presenter just to check your screen.
Okay.
Okay. Okay.
Well, that works.
Yes, so you're good. Excellent.
Thank you very much.
No worries.
Hello.
Hi, Donya. I can make you now a presenter as well to check your screen as well.
Hello.
Hi, can you hear me?
Yes, I can hear you. Can you hear me?
Yes, great. I just made you a presenter if you want to check your
Yes,
screen.
I would like to check.
Yeah. Excellent. We can see your slides as well.
Okay.
Great.
That's all?
That's it. Yes, yes. Just to ensure that you can share them, because if anyone is on web mode, I'm not allowed to make them into a presenter, so they cannot share their slides. That's the issue. But now you connected correctly, then it's fine. Then you can. Yeah. Great. Thank you.
Okay. Thank you.
Hi, everyone. If our speaker is here, Charbel, I cannot see our guest speaker at the moment, our invited speaker. So should I introduce the chair of the next session? It would be Professor Charbel Afif. I cannot see the first presenter. We can perhaps go to the second presentation if they're not here yet, but I will let Charbel introduce the session.
Okay, so thank you, Eleni. So the session, as you all know, is about air pollution sources and impacts, mainly focused on the EMME region. Normally we have Dr. Gael Uzu as an invited speaker, but I think she's not here yet. So meanwhile, we will begin with our oral presentations, and whenever she arrives, so practically we will follow directly with her presentation. So meanwhile, we will have the presentation called Arabian Incense Burning as an indoor source of fine particles, abundance, and oxidative potential. So, and this presentation will be delivered by Yuan Zhu. So, Eleni.
Hello.
Hello. How are you?
Yeah, can you hear me?
We can hear you now. I will share their slides on their behalf because they have some.
Yes, please.
Just share my screen.
Sorry.
Like before, our presentation, we have like around 7 to 8 minutes of presentations, and then we'll have 1 or 2 minutes for questions and answers. Whenever you're ready, please feel free to begin.
Okay. Hello, everyone. So this is actually Sankong Liang, the first author ranking here. So I'm sorry that Professor Chen have some national events to attend, so he cannot make it. And my colleague Li Yuan, who has been already working in China mainland, and there is some like IP problems, so she cannot log in the system. So I will be the presenter for this interesting work entitled Arabian Incense Burning as an Indoor Source of Fine Particles, Abundance and Oxidative Potential. Okay, so could you please, I can do it myself or, oh, okay, cool. So yeah, so before I go into the specific study, I would like to briefly remind everyone why air pollution is such a big health issue. So according to the World Health Organization, the combined effects of outdoor and household air pollutions are linked to about 7 million premature deaths every year worldwide. So both ambient and indoor sources are critical when we think about people's real exposures. Okay, so can we move on? Cool. So here we look at the impact of life expectancy. It was reported that 5 particulate matters, PM2.5, can shorten average life expectancy by around 1.5 years in many polluted regions, including many in the Middle East. Yeah, please move on. In Saudi Arabia, hot burning is a very common cultural practice. A recent cross-sectional study surveyed more than 1,600 adults and found that about 98% of the participants report using bahut indoors, and roughly 3/4 of them ignite with the charcoal. So this is not a niche source. It is something almost everyone is exposed to, often on a daily basis. Yeah, please. Yeah, okay. So given how widely it is used, an obvious question comes up. What kind of particulate matter does it produce, and what does that mean for health? In this work, we have two main objectives. First, we wanted to characterize the particle emissions from bar-hole burning in terms of size distribution, mass concentration, and chemical composition. Second, we aim to assess the oxidative potential as a measure of the potential health impact using both a cellular DTT assay and cellular assay looking at the reactive oxygen species generations and the cell viability. Yeah, please. Okay, so briefly, we can look at the schematic. In brief, you use purified relative humidity controlled compressed air and a chamber system to burn bar-hole to mimic the daily utilizations in a controlled way, so we can have better quantified results for some insights. So we collect filter samples and at the same time measure the size resolved particle number concentrations with an SEMS, a specific instrument. For chemical analysis, we use ultra high performance liquid chromatography coupled with a high resolution orbitrap mass spectrometer, which is a state-of-art analytical instrument for the characterization. Yeah, next page, please. So first, I want to show that we select three types of typical bar-hole products that represent a wide range of products we can find in the commercial market. So type 1 is a more traditional or money style blended containing Planck incense. So the type 2, which stands in the middle, is a premium formulation with oud, amber, and sandalwood. And the right-hand side is a more modern floral woody perfume blended. While these selections reflect a range of product types, detailed compositional information for commercial products, bar-hole products remain limited. Yeah, next, please. Okay, so this figure we show the size resolved particle emission from bar-hole burning. Overall, we see a bimodal number distribution. Here, there is a dominant peak at around 30 nanometers and a second peak around 160 nanometers, which is roughly 40% lower than in number. So ultrafine particles, UFP, those below 100 nanometers, and accumulation mode particles dominate the number and mass emission respectively. Among these three products, type 2 tend to produce the highest particle mass emissions. Yeah, please. Okay, so if we look at the temporal profile over a burning event, we will be able to see a synchronized formation of ultrafine particles and accumulation mode particles, let's say located around 100 nanometers. They rise and evolve together. In terms of the emission rate, bar-hole mass emissions are on the order of 700 to 2,500 micrograms per minute per gram of material. This places at the upper end of typical indoor sources, including tobacco smoke, incense, moisture, candles, cooking, and e-cigarette. Ultrafine particles dominate the number emissions exceeding the cigarette levels. So to understand what control these emissions, we separate the bar-holes into two, wood residual and hexene-soluble extractives, which are mainly oils and other non-polar components. Using the FTIR-ATR, which is spectroscopy technique, we found that the oil extracts show much larger spectral variability than the wood residue, particularly in regions associated with CO bond stretching and other functional groups. Yeah, please go ahead. Yeah, more interestingly, when we related the particle emissions to hexene-soluble extractives, we find a nonlinear relationship, which is very surprising. Even at zero extractive, there is a baseline emission of around 0.5 milligram per minute per grams of material. As the hexene-soluble extractives increase, the emission rise more rapidly, steeply, following a power law type relationship. We also test a sample wiping strategy. That means removing the oil, physically removing them from the surface of the chips. by using the napkins with the solvent. The tissue wipe chips emit only 50 to 76% of the original PMS. So emission dropped by roughly 24 to 50%, which is significant. Practically, that means it means that choosing drier, more metal-looking chips or those leave a smaller oil strain when pressed with a tissue can potentially significantly reduce the PM emission in the daily utilization practices. Yeah, please. Okay, so due to the time limitations, I want to sum up what we have been finding so far. So the hot burning is a strong indoor source of fine particles, okay? Comparable to cigarette, which is like kind of not a very well-known scientific message. So these particles stay reactive indoors and may enhance the oxidative stress upon the daily contactions. So because of the emission increase with oily extractive, the simple squeezing or wiping the chips can cut the PM and overall oxidative dose by about 1/4 to 1/2, which is very important. And this is also an important message that we want to deliver some practical implications beyond the scientific findings. Okay, so thank you so much for your attentions, and I'm happy to take any questions. Thank you.
So thank you for the presentation. In fact, it's a very interesting topic, as you said, because this is widely used in the EMME region. We have also one question from Mark. He says, so thank you for the presentation, very interesting. The DTT values were based on online or offline measurements? And then he says, so a second question, what type of cellular assays were used?
Oh, okay. Sorry about it, because of time limitations, I have no time to cover this. So for the DTT, we measure for offline basis. This is because we want to facilitate an internal comparison between, the chemical assay and the cellular assay. And for the cellular assays, we use the microphage. So microphage, upon exposure to any oxidative materials, there is potentially, damage in the membrane and excretions of any signal processes. And we basically also monitor the viability of the cells as an indicator for the oxidative stress. And interestingly, we found that even though we exposed to those hot burning particles, which is not typically considered very hazardous, we still found there is the death of the macrophage, which indicate the potential, biotoxicity. So this will come with the later, I guess, the manuscript we have been preparing. Yeah, thank you for raising this. Thank you.
Great, thank you. So any more questions?
There are not any other questions in the chat.
Okay, so let's hear it from Mark. So Mark Fadel.
Yes, hello. Can you?
So Mark Fadel will be talking about source apportionment to PMF to PM 2.5 oxidative potential. So Mark, the floor is yours. Thank you.
Okay, thank you, Sharbel. Can you see my presentation?
Yes, we can see it.
Okay, perfect. So hello everyone. I am Marc Fadel from Université du Littoral Côte d'Opale in France, and today I will be presenting the link between source apportionment and PM 2.5 oxidative potential with a special application in the East Mediterranean region. So as we all know, and it has already been mentioned, that the Mediterranean region is considered as a hotspot of climate change. And one of the countries that is highly affected by this outdoor air pollution is Lebanon. This country is situated on the eastern basin of the Mediterranean Sea, and is considered as a highly urbanized country with more than 85% of the population living in urban areas. Most of the studies that were previously conducted in Lebanon regarding air quality were focused on urban areas and specifically also on short time series. So this is why in my presentation today, I will be presenting two projects that were led by the St. Joseph University, aiming to identify the major pollution sources in the country and to quantify the contribution of the sources to the value of the oxidative potential. So in order to do that, we have chosen sites from different typologies. So first of all, we have the FA site, which is a rural site under the influence of cement plants. The HR site, which is an urban site with dense road traffic. The ZK site, which is an industrial site, which encompasses the biggest power plant in Lebanon running on heavy fuel oil. And the USG site, which is mostly a suburban site, and it was like the St. Joseph University campus. So these samples were collected on a 24-hour basis, and we have around 300 filters that were collected for the overall campaigns, and all the samples were chemically characterized for their carbonaceous fraction, around 80 organic compounds, elements, and water-soluble ions. Some of the species that were characterized were combined in order to do the source apportionment by PMF by combining organic and inorganic species. So here I'm presenting the results of the source apportionment for the 4 sites. So we have identified approximately 11 to 12 sources per site. And here on the left, we can see that the average PM2.5 concentrations during the campaigns were very similar. So first of all, we can see that the sources that highly contribute to the PM mass were ammonium sulfate and crustal dust, contributing between 34 and 47% of PM concentration. We can also see that the traffic emission is an important contributor, and we have the highest contribution explained or presented in the site that is under the traffic influence. And finally, here we have the heavy fuel oil combustion with the highest contribution for the site that it is under the influence of the power plant. And finally, for the biomass burning, we have a contribution varying between 3 and 5% between HR, ZK, and FA, and the higher contribution found in USG due to a bushfire event that happened during the sampling campaign. So what about oxidative potential? So a brief definition. So the exposure to PM, it creates an imbalance between the production, between the reactive oxygen species and the cellular antioxidant capacity, leading to oxidative stress. So the oxidative potential is presented as the ability of this PM to deplete antioxidant molecules. And in our study, we have done the measurements using the ascorbic acid and the DTO-tritol assays. So as we can see here in this table, we have the values of OPAA and OPDTT for the 4 sites, and we can see that the values are quite homogeneous. And we can see also that these values are close and similar to those to other studies found in urban and industrial areas. We wanted to go further in the interpretation of these values of OP, and we wanted to understand which sources have the highest impact on the oxidative potential. So this is why we have applied a multiple linear regression model aiming to determine the values of beta, which are considered as the intrinsic OP values or the OP values that are specific to an emission source. So briefly to present the results, so for each graph, the first bar represents the contribution of the sources to PM2.5, the second one to contribution to OPAA, and the third one for OPDTT. So first of all, very surprisingly, the crustal dust source, which shows a considerable contribution to the PM concentration, was not the one driving the OP values, with a contribution varying between 0 and 9% for OPAA and between 0.1 and 7% for OPDTT. However, for example, we can see that biomass burning that have a small contribution to PM shows a considerable contribution to OP, with values varying between 8 and 30% for OPAA and 4 and 41% for OPDTT. One of the important conclusions that we have also seen in this study is that local anthropogenic sources, namely traffic sources, biomass burning, and heavy fuel oil combustion, are the sources that highly contribute to the OP values, with values varying between 29 and 75% for OPAA and between 36 and 80% for OPDTT. And it's important also to know to say that secondary sources has also a non-negligible contribution to the OP values. So to conclude on this presentation, so the aim of this study was to collect filters in order to do source apportionment using a source-oriented model, which is the PMF, in order to identify approximately between 11 and 12 sources per site. We have tried to do the link between the oxidative potential and the sources, and the main result that we have is that local anthropogenic sources, namely road traffic, heavy fuel oil combustion, and biomass burning, they had the strongest influence on OP indicators. Finally, I would like to thank all the contributors and the financiers of this work, and I want to thank you for your attention.
So thank you, Mark, for your presentation. Very interesting. So we have already a question in the chat box, but I have a question also for you. How many studies on OP were already conducted in the EMME region and the Middle East and so on?
In fact, in the region, there are very few studies that have identified or measured OP, or at least measured OP for OPAA and for OPDTT. So this is why we consider this study as very original, because it was like the first study combining different sites with different measurements of OP, and that tried to do the link between OP and the sources. So we can find a lot of studies doing that.
So normally, in which countries these studies were, in general, like were conducted, other than Lebanon, that you presented?
Okay, so I think, and I'm not sure, I think that the study was done in Qatar regarding the oxidative potential measurements. I think that we have also some information about Athens, and I think this is it.
Okay, and there's one currently that is being conducted for Egypt, for Cairo also.
Yes, exactly.
Yeah, okay, thanks. So the question in the chat box says, so thank you for your presentation. Did you do the analysis on ISO concentration or not? And if you can also explain a little bit, in fact, the difference and what this will imply, whether it is ISO concentration or not.
Okay, so in fact, in our methodology, so when we try to develop this these OP measurements, we didn't work on ISO concentration. So if you want to explain a little bit about the ISO concentration, it's like considering that we have the same PM concentration in all samples. So for example, we use 10 microgram per milliliter or per microliter or 25. And what we will change in the extraction methodology is like the dimension of the filter that we want to use in order to do the extraction. So so sometimes they privilege the use of ISO concentration in order to try to compare our results with the results of other studies. So this is why working on ISO concentration might be important. However, if you want to compare the data, for example, from different sites using the same methodology, like for example what we have done here in this work, it was not necessary to work on ISO concentration, because the idea is like to compare the data between our studies, our sites.
Okay. So thank you, Mark, for the presentation. Very interesting. And so now we go back to our invited speaker. So Dr. Gaël Ouzou from the Institut des Géosciences de l'Environnement from France. And so thank you, Gaël, for accepting to talk in this workshop. And she will be presenting, in fact, she will be talking about exploring oxidative potential of atmospheric particles in Europe and exposure scenarios. So, Gaël, please, the floor is yours.
Thank you very much. I try to share my slides. I can't. Can I share? Can't share.
Yes, you're the presenter now.
Yes, but when I'm not allowed to share. Ouvrir préférence système. Oh, it's very. Otherwise, I sent my presentation to Eleni this morning. I don't know if she got it.
Okay, so normally, yes, she has it. Eleni, can you please share the presentation for Dr.
Just a second, I'm trying to find it because I'm not sure I have it, but I'll double check. Just a sec.
I can send it to you, Charbel. It's not. It's okay. Again, my Mac saying that he would need to restart again to allow you. Oh. Usually, you should have it now. It seems that my security system of my computer doesn't allow me to share again. Do you have it? I send it.
To me or to
you again.
To me, yeah, I'm checking. I didn't get it yet. Maybe like 30 seconds.
Yeah. I can try again in PDF. Can be fast. I have sent it also in PDF because it's quite heavy. Really. I send it again. It's done. Can you see it?
I'm just, I didn't receive it yet, so.
Okay, so would you like that we would go again ahead for you, waiting for my presentation, or that I can restart my computer and you go first and I go back?
I just received it. Okay.
Okay.
Okay, received. So here it is. And now normally you should be able to see my screen.
Thank you, Charbel.
Oh,
yes.
Great.
Yes.
So guys, the floor is yours.
Yes. Sorry again for this live disaster of matter of computer. The idea today, so Charbel invited me to present you our last paper in Nature exploring oxidative potential of PM variability for European regulation, but he also asked me to introduce you a bit of OP modeling on where we are now. So I will present on behalf a huge team, and it's a pleasure to be today with you. Please next. So the idea we will have a matter, I think, because it is not the complete slide, but I will do my best. Yes, the idea is that we have, you know that air quality is posing risks for health, but it's also a matter of between short term and long term. We know that one of the key biological mechanisms is, it's going too fast. Charbel, I don't know if you can go back. Can you just go? Yes, here we are.
Yes. Okay.
So the idea is that we know that one of a key biological mechanism relies on oxidative stress, which is at the origin of many outcomes like cardio, vascular-respiratory disease. But we know also that many physiological chemical properties are related to their toxicity, not only the quantity, but also the composition, the size, specific surface and solubility. And one of the good news that happened last year that we had a revision of our European regulation which has lowered many PM mass concentration, but also has introduced new recommended measurement on urban and rural supersets. And among this new recommended measurement, we have now oxidative potential in the game of this recommended variable, and where oxidative potential look at the PM intrinsic capacity to induce oxidative stress in the lungs. And it has been recommended to do at least 2 acellular complementary measurements, among them OPAA and DTT. Please, next, Charbel. So the idea of this paper, the main objective was to look at the added value of OP in the European landscape, but also how should we set OP standards, and do we have, are we able to set mitigation action to reduce the PM exposure in terms of OP? This is why we have published 10 years of measurement among 43 European sites, sitting in 10 countries, and allow among 5 site type of typology, among them traffic, industry, urban, suburban, rural. And we have analyzed all of these OP assays for OPAA and OPDTT with an homogeneous protocol, all extracted at ISO concentration to be able to compare them, and for 3 PM size fraction. Next, please. And here are the first result. Here we have the measurement. If you can click a bit, yeah. We have, so on the top of this slide, we have OPAA. On the level, we have OP DTT per volume. And so you can see some very large difference between the OP levels that are displayed with the bar plot, in contrary to their relative PM mass, which are the black dots. You can see also some big difference between PM10 and PM2.5 and PM1 levels. But if you have only, probably the most important things to, as a home message of this graph, is to remember that we have a factor of 3 between the rural location and the traffic location in terms of OP levels. Please, next. Again, for the next slide, please. Yeah. So now we will go for a bit of focus. So please, next, Charbel. And so it's important to have, first of all, an OP for the exposure. The OP metric is done by volume, also to mimic PM mass concentration, and to be able to have an idea of what is an OP per inhalated of cubic meter. But it's also very interesting to look at the OP per mass, which relates to the oxidative burden of 1 microgram of PM. So when you look at so it's very interesting to access this information per sources. because you can have the oxidative burden of one sources and you are able to discriminate them. But coming back to the OP per mass for the site typology, you can see on the right on this graph that we are able also to see that urban site and, for example, traffic site, their OP per mass is very different. It is the same, if you can click again, Charbel, we were also able to discriminate between traffic site and industrial site, but also suburban sites that are have a long range of values. And lastly, if you can click again, we will have the rural site that's still above other site typology. So click again, please. We have shown that OP was able to distinguish site typology or site types that are characterized by really specific sources mixes. And it is what is also interesting is that OP is doing that where mass fail, because a lot of in Europe, all of these site typology have as a middle PM mass of between 20 and 25 microgram per cubic meter. Please next. Yeah. So this is where we can do an interesting link with the OP modeling, coming back to this intrinsic OP. So this intrinsic OP can be also accessed for every sources when you have your OP measurement, your PM speciation, and then you can do a PMF as has done previously Mark. And through this PMF, you can apply a linear inversion after that, where you will obtain your intrinsic OP for every one of your sources that you access during your PMF. And this intrinsic OP, we then develop a collaboration with the team of Gilles Fauré in LISA, where we were able to try to find some correspondence between this our factor of PMF, our profile, but also the snap of the emission sources in the SHIMMER model. So if you can click, please. Yes. So we have found a way to model the PMF sources using the model tagging in SHIMMER by doing some correspondence between their PSAT and our by rearrangement between our chemical profile and their PSAT contribution. And thanks to this, we were able to assign each an OP, an intrinsic OP per sources also in SHIMMER. And if you click Charbel, we have done some simulation for the whole France, and we can go, if you click again, we can investigate for each sources what is its contribution for France regarding the PM10 on the left and on the right for the different OP. So you can see that biomass burning is something that is popping clearly strong, as previously mentioned by Mark. Same for traffic. You can see the big urban areas popping also. Please next. Okay. You can see also that when we look now at long-range transport sources like nitrate-rich or sulfate-rich, they come in the picture with PM10, but for OPAA, they are almost blind. They have a contribution of nearly zero. But it's not the same for OP DTT, that is also much more correlated with the PM mass. So this is what I wanted to show from this study. And now The idea is to show you how we can now extract some OP exposure scenarios. So we can use all the average level in every site in Europe, or we can take some average level also in from the simulation from the chemical transport model. Can you please click again? Yeah. Yes, and again one. Yes. So the idea is that to do that, to do some exposure scenarios, typically you need some dose response curve for OP, for example, for mortality. And this is something that is under study, but that has not been established. So to do some exposure scenario, when you do not have this kind of dose response, the health impact assessment goes through reference value based on observation in the less polluted site to get the total burden of pollution related to anthropogenic activities. So to have reference values for OPDTT, we took some very low anthropogenic pollution scenarios. So we grab the lowest values that we get in rural sites. And we had also intermediate scenario. Can you please click again? And we were also able to extract some, it was back, sorry. We were also able to extract low urbanization scenarios by grabbing some cities that were less polluted than our top podium. And this is how we were able to get some two reference value to apply different scenarios that I will now show to you. Again, please click. Yes, again. Yes. So the idea is, now that we have these reference values, we are able to quantify the effect of the reduction of the most oxidant sources of OP level to discuss the most also effective PM reduction strategies. So this matrix is made from, on your axis, you have the biomass burning factor from PMF, but also the traffic factor from PMF in urban context. It is some merge, it is some average PMF factor for several European cities, and we have transformed this. We have transformed. The idea is how much of traffic factor do we need to reduce to achieve the OP reference level we would like to achieve. So we have shown, for example, that if we take the scenarios with the least polluted urban sites for 1.6 nanomole minute per cubic meter, we need to decrease by 25% PM10 from traffic, or 15% from PM10 from both biomass burning and traffic together. And please click again. But if we would like, for example, to compare with WHO recommendation, we would need to diminish by 65% of both traffic and biomass burning together. So please click again. This matrix can, we have different metrics for rural environment, for industrial environment, for urban environment. And regarding the different site of typology, you can apply different emission reduction approach for your type of environment and to achieve optimal improvement in both PM and OP in the future. So again, please click, yes. So in this talk, we have looked at the added value of OP, that we have shown that OP was able to diminish between site typology. We have also shown through exposure scenarios that we were able to to obtain OP reference value based on observational data, based on more than 1,000 observational data in low polluted sites. And this could serve as an initial step to target better OP levels. And we have also shown that we can set up PM reduction strategies based on the specific oxidant sources, namely biomass burning and traffic, to reduce both OP and PM mass concentration. So if you need more insight, you can access these two studies. And I would like to have a special thanks to yes, we were many in these studies to be able to publish such kind of data set. Thank you very much. I'm done.
So thank you, Gael, for the very interesting and lovely presentation.
Sorry for speaking every 15 seconds. Yes.
No, it's fine. Don't worry.
It's not easy, you know. Yeah.
It's fine. Please, if you have any questions, please post them on the chat. However, I have a few myself. So first, regarding the two acellular tests, OPDT and so normally there are different tests. It's not the only ones that normally that they are used. Yes. So do you think that these two, like in the future, will be sufficient to describe the OP and the interaction of OP with the particles? That's one.
We have about, in the landscape of OP community, I would say that about 10 OPSA are available. Some of them are on the decrease, some of them are on the rise. DTT is for sure the most used because it is also the oldest. OPAA made also is proof, but regarding OP assays on the rise, I would mention OPOH, which is not an indirect measurement, but a direct assessment of the hydroxyl radical. But this test needs also a bit of standardization, but has already shown interesting epidemiological outcomes in Los Angeles. So I would say that in ERA Urbans, we have done some service tool to some recommendation for the OP community. The idea is to say that we have tell people to use at least or OPAA or OPDTT because plus another one in complement, because at some point you need also to be intercomparable with other studies, and if all people, for example, commit to do OPDTT plus something else, at least we will have OPDTT to compare. But OPDTT, what we see now is that OPDTT is probably more associated with long-term and chronic outcomes, where, for example, OPAA, what we have seen recently is could be more related to acute event. So I think the story is not over, you know. Probably for years we all wishes that it could be something that one could be the best one, and but probably we will have to use one also regarding short-term and long-term, because it's not only a matter of what OP and sources says, but also how health answer to OP. And regarding this pathway, it's only the beginning of the story. We have only 20 epidemiological studies crossing OP, and so it's not sufficient.
Okay. Okay. So there's a question. Thank you. So Gael, there's a question from Ricardo Fonseca. So he's saying that thank you and very interesting talk. Is the ultimate goal to account for OP and air quality index given its health-related impacts?
Can you?
So is the ultimate goal?
Yeah.
Is to account for OP and air quality index since it has health-related impacts. And I will add a little bit on it. How much mature the OP index is, and how can we take it like now as the only indicator? Can it replace like many other indicators? And
so the idea, I think OP will complement PM mass, but we need both of them. You need the quantity and you need the quality. Because extreme event can happen because of the quality, but what we see that there is no doubt that over decades, what is making a huge difference is the chronicity of your exposure with PM mass. Where PM mass fail is for short-term events, but for long-term events, the mortality dose response is well established, and there is nothing to that OP will just probably refine something at some point, but will not be a game changer. I think OP is very important for acute events where, for example, PM mass can also fail. We have seen, for example, this is something that can be, we have a lot of examples. For example, in our Alps, in spring, we can have a lot of snow that came people to put a lot of salt in the road, and we have huge events. We can have PM10 up to 100 microgram per cubic meter, but it's only salt, and salt has no OP. So it can be a game changer in these kind of things, but on the long term, I'm pretty sure that PM mass remains very important, but for an air quality, a day-by-day index, I'm pretty sure that OP will help a lot.
Okay, so thank you, Gael, for your response. Yeah. I still have some questions, but I think time is running.
You can contact me. Yes, now you have my presentation, Charbel. Sorry again for the nightmare of troubleshooting of connection.
No, don't worry. Thanks a lot, Gael, for all the insights you gave. Very interesting talk. And so now we will move to Nancy Fakhre, talking about PM 2.5 sources in the Eastern Mediterranean, Middle East city of Beirut, chemical characterization and contribution to ambient concentration. So Nancy, if you can share your screen, please.
Can you see my presentation?
No, not yet.
Can you see my
now,
presentation?
yes. Now, yes.
Hello, just one moment. Just move this one. Okay, this one. Okay, hello everyone. My name is Nancy, and today I will be presenting the PM 2.5 sources in the East Mediterranean Middle East city, Beirut. So Lebanon is a Middle Eastern country with a population of more than 6 million people. Beirut is the capital and largest city in Lebanon. Greater Beirut area is a typical agglomeration in the EMME region. Previous studies conducted in Lebanon reported that the average PM 2.5 concentration are 6 to 10 times higher than the WHO recommendation. So the goal of our research is to determine the chemical composition and identify and quantify the sources of PM 2.5. So the first step to achieve our goal consists of collecting the samples from the location in Beirut. So samples were collected at two sites, Harish and USG. So Harish is an urban site and USG is a suburban site. Heritage is characterized by a high density of residential and commercial premises, while USG was located on the roof of the Faculty of Science at St. Joseph University. The distance between the two sites was 5 kilometers. After that, a detailed chemical characterization, including the analysis of EC and OC, water-soluble ion, major and trace elements, and a large suite of organic compounds was performed. PMF was then used to identify the sources and their contribution. So let's focus for a minute on what PMF is. So PMF is a multivariate factor analysis tool that decomposes a matrix X into two matrices, factor contribution and a source profile. The goal is to solve a chemical mass balance between the measured concentration and a factor profile while minimizing the residual between the modeled and measured concentration. To ensure the robustness of our result in PMF, several quality control criteria were evaluated. For example, the residual of species, the assessment of model stability through bootstrap and displacement, etc. So for our results, the average PM2.5 concentration found at the two sites were approximately 30 microgram per cubic meter, which is 3 to 6 times higher than the WHO guideline, depending on whether we are considering the old standard during the sample period or the new applicable WHO guideline. So once we have completed the chemical characterization, we have decided to investigate the methodology we want to adopt in our work to identify the sources and their contribution. So one central question was, what species should we include in PMF? So the majority of source apportionment studies are carried out using OC, EC, ions, and element as input. Recently, some efforts were made to incorporate specific source organic markers in PMF. However, they have included the organic species as a family. For example, the sum of odd alkane. And in fact, in one family, you might find different tracers for different sources, which is not the goal of our research. So if you take the example of alkane, if you look at C15 and C16, they might give us the information regarding the natural source from the sea. C20, C21 regarding diesel emission. So if we add the alkane, like what the literature have been doing, we are missing important information on important sources. So in our work, we have tried to assess the importance of including specific organic tracers in PMF, as we have a full laboratory equipped for the measurement of a large suite of organic tracers at St. Joseph University in Beirut. So we decided to do the exercises to see whether we should adopt the traditional methodology by including OC, EC, ions, and elements, or we should add specific organic tracers in PMF. So for this reason, we have done 2 PMF runs, with organics and without organics. So when we compare the PMF results with and without organics, 6 common factors were identified by the same tracers. And also 4 additional sources were identified based on the inclusion of organic tracer. However, how do we assign a source to a chemical profile? Let's take the example of vehicular source. So if we compare the 2 PMF approaches, shows that including organic markers in the PMF refined the estimated contribution of vehicular emission. So in PMF traditional, the vehicular emission was identified in 1 factor. While in PMF organic, the vehicular source was divided into 3 specific sources. So I still have the source that has the copper and antimony, but we have 2 more additional factors, 1 for the lubricating oil and 1 for the fuel combustion. So in conclusion, we can, by adding the organic tracers, provide us a more detailed and a more complete source apportionment and allows us the resolution of more and additional sources. Therefore, the methodology including specific organic tracer in PMF should be adopted. So if you look at our results, we notice that not all the identified sources have the same priority for mitigation. So several sources such as dust storm and marine originate from natural sources which cannot be mitigated, making the WHO guideline of 5 micrograms per cubic meter unreachable in Lebanon. On a national level, to effectively reduce PM, this work has identified several local controllable sources, such as diesel generator, road transport, and biomass burning. Our study have also compared the PMF results to the national emission inventory and global emission inventory. So the comparison shows that road transport emissions are underestimated in both national and global inventories. So overall, none of the emission inventories is ideal at present, but the national emission inventory is better to use for air quality model and health risk assessment. So in conclusion, our study has provided a detailed chemical characterization and source apportionment of PM2.5 in Beirut. And also the PMF analysis showed that including specific organic tracers improved the resolution of sources, allows the identification of additional sources, and overall the use of PMF with organic tracers combined with careful consideration of filter to species ratio offer a robust methodology for understanding urban air pollution and supporting air quality management in Lebanon. Thank you for your attention.
So thank you, Nancy, for the presentation and for the recommendation, let's say methodological recommendation. Any questions from the audience to Nancy?
I can't see any in the chat. Okay.
So Nancy, I have a question for you regarding which tracers, organic tracers, should be input. Is it like all of them or just a few?
We should include in PMF all tracers that are specific to a certain sources. For example, if you want to have the cooking emission, we should include specific fatty acids. If you would like to have sources like diesel emission, we should add specific tracers from alkane, which are C20 source C21. So we should include specific source tracers for each source. The more we add tracers, the more we have sources in PMF.
Okay, so you're saying that we should add all the tracers that we have.
Exactly,
so
but we
have the maximum number of sources.
Yes, but as I mentioned in my last slide, we should always respect the filter to number. So we should always have a ratio of filters to number of species input of 3. So we should always respect this guideline. Okay, so thank you, Nancy, for your presentation. And so now let's move to Yesubu for a presentation on satellite observations and modeling of air pollutant sources and their impacts over the Arabian Peninsula. So Yesubu, so the floor is yours.
Yesubu, you're muted, so if you can unmute your microphone, please.
Thank you.
Now we can hear you.
Can you hear me?
Yes, we hear you. Just please make sure to have it full screen. To have your presentation full screen. Great, thank you.
Yeah. Thank you. Thank you for the organizers for providing this opportunity to present our work to the scientific community. Myself, Yesubu Yeragunda, I am a postdoctoral fellow at NGO's lab at Khalifa University, Abu Dhabi. Today my talk is satellite observations and modeling of air pollutant sources and their impacts over Arabian Peninsula. So we know that in the Arabian Peninsula we have very sparse monitoring locations of these air quality variables. So we need to rely on satellite observations only. So we know that this Arabian Peninsula is shaped, air quality of Arabian Peninsula is shaped by frequent dust storms and human activities. So for monitoring of this air quality over Arabian Peninsula, we need to rely on satellite remote sensing. If you rely only on satellite remote sensing, we are unable to know the what process is to drive these high pollution events. So we need to rely on, for this we need to rely on chemistry transport models. So today my talk, I will talk on two topics. First one, examining its spatial and temporal patterns of NO2, SO2 over Arabian Peninsula. Next one, so I am going to evaluate WRF-CHEM model over UAE region. For this, I have used various satellite instruments. For fulfilling first objective, I have used OMI satellite data. For this OMI satellite data, we have a large data from 2005 to 2023. For evaluating WRF-CHEM model, I have used TROPOMI satellite data for NO2, ozone, CO, and MODIS for AOD. So this is the climatological long-term average spatial distribution of NO2 and SO2 from OMI satellite from 2005 to 2023. So I have used for arriving this spatial distribution, I have used daily average concentration of these pollutants, and these daily concentrations I have aggregated into monthly average concentration, and that monthly concentration I have aggregated into annual average concentration. This is the 19 years average concentration of NO2, SO2 over Arabian Peninsula. So here also superimposed of various sources of SO2 over this spatial concentration like power plants, smelters, oil and gas facilities over this Arabian Peninsula region. And also here in this study I have find how these two important air quality variable changes over time. This shows the monthly and annual variation of SO2, NO2 over Arabian Peninsula region. Here I have chosen domain 10 to 40 north and 30 to 60 east. We look at this annual variation, it shows that NO2 is changed. NO2 is changed from 2005 to 2023, but SO2 is changed. The change is very small in SO2 concentrations. Whether this variation is significantly or not, I have find that using trend analysis. This is the annual trends calculated over Arabian Peninsula using ordinary least square method over the deseasonalized time series of domain averaged NO2 SO2. So after desaligning the time series, I have applied ordinary least square method over this desaligning time series to find out a slope and breakpoint. After finding the slope and the breakpoint, I found that 2008 is a breakpoint in the case of NO2 and 2011 is a breakpoint we find in case of SO2. So whether these trends are significant not or are monotonically increasing or decreasing, I have found out using Mann-Kendall-Thielsen slope. After that, so I have configured weather research forecasting model over Arabian Peninsula with 3 domain setup. Second domain is centered over UAE region and various meteorological observation locations and aeronaut locations and ways locations I have used to evaluate these model simulations. In this WRF-CHEM, we have used anthropogenic emissions, biogenic emissions, and Mozart chemical mechanism and WSECM chemical boundary conditions to feed into the model. Before evaluating my chemistry evaluations, I evaluated first meteorology over the second domain UAE regions. For evaluating meteorological observations, I have used airport station data and also NCM dataset for 2-meter temperatures and wind speed, and also I have used ERA5 data for evaluating 2-meter temperatures and planetary boundary layer height. After looking at this meteorological evaluation, I found that the model is able to capture all its diurnal variability and its variation of these meteorological variables. After getting the confidence on the meteorology, I have evaluated these model simulations with satellite observation tropomy. This is the tropospheric column NO2 concentration between tropomy and WRF chem. So before comparing this spatial comparison between these two data sets, the model simulations I have smoothed with averaging kernel and a priori matrix provided by the satellite data, and it shows that the NO2 concentrations are satisfactorily simulated over this study region. Sorry. Sorry, I have missed another slide. I have also actually looked at the total column of CO and total column of ozone over this study region. It is also shows the satisfactory performance over study region. So conclusions. So from the OMI, spatialist distribution showed higher concentration over urbanized and industrialized regions, and also prominent hotspot regions are concentrated within the 9 target regions. The emissions over these areas are primarily driven by anthropogenic activities, including oil and gas productions and industrial operations and power generations and transportations. For my second objective, so meteorological parameters were simulated well by the model. For temperature, generally it is within 1 degree C. WRF-CHEM showed a strong correlation with TROPOMI satellite datasets. For NO2, a lower skill of simulating total CO columns, accurate modeling of tropospheric NO2 and SO2 columns. Thank you.
So thank you, Yusufu, for the presentation, especially that in this region, we do not always have access to measured data from air quality monitoring networks. So any questions from the audience, please put them in the chat box so that we can ask them to Yusufu. Eleni, do we have any?
I can't see
questions?
any new questions, unfortunately.
Okay. So Yusufu, I have a question for you regarding the time series. So did you conduct your modeling over the entire time series that you showed regarding the satellite data, or was it only over a specific year over the UAE?
Yes, so over each specific year only, that is 2022, for 2 seasons, summer and winter.
Okay. Okay. So you only conducted what you showed us. So you didn't do in the background the whole time series. Okay. I was a little bit interested to see if you saw like any special changes in air quality, whether from the satellite data or more also specific from WRF. Okay, so thank you, Yusufu. And so now we can also move to Eliane Farah. So Yusufu was from Khalifa University at UAE, and now Eliane is from St. Joseph University of Beirut and from the Université du Littoral Côte d'Opale in France. She will be talking about air pollution in Greater Cairo, so minor PM2.5 sources with significant health risks. So Eliane, the floor is yours. Thank you. Yes, we see your slides. That's fine. Please go ahead.
So hello everyone, I'm Eliane Farah, and today I will be presenting my work, Insights into Air Pollution in the Greater Cairo Megacity, Minor PM2.5 Sources with Significant Health Risks, done in collaboration between St. Joseph University of Beirut in Lebanon and Université du Littoral Côte d'Opale in France as part of the EMME-CARE project. So the PM have drawn much attention in the Mediterranean region, which is considered as a hotspot of climate change and air pollution. The Greater Cairo area located in this region is considered as one of the most polluted megacities in the world. In 2019 and 2020, and according to the Central Agency for Public Mobilization and Statistics in Egypt, Greater Cairo area featured 25 million inhabitants besides 4 million vehicles running on the streets. Faced with this problem, the implementation of public policies to manage air quality in Greater Cairo area has become a major challenge since, again, we have a few studies showing and focusing on Greater Cairo area. So for this region, the EMME-CARE project was conducted. This project was conducted by the National Research Center, LAMP Laboratory, St. Joseph University, Cairo University, LISA, the Cyprus Institute, Université du Littoral Côte d'Opale, Mainz, Douai, Port Said University, and the American University of Beirut. This project aims at assessing the sources of atmospheric pollution and the health risks associated with human exposure to PM2.5. For this reason, a sampling campaign has been conducted. So in the following, I will be presenting the sampling campaign of PM2.5, the experimental methodology, the results of the source apportionment and the health risk associated with PM2.5 sources, and I will conclude at the end. So the sampling campaign has been carried out at the rooftop of the National Research Center in the Greater Cairo area in Doki, and at the rooftop, and the PM2.5 samples were collected on a 24-hour basis every day using a high volume sampler. 59 samples and 2 field blanks were analyzed. Once the filters they were sampled, they were stored at -20 degrees till the analysis. The sampling site is situated in proximity to significant industrial regions, including Helwan, Tibbin, and Shubra Al Khaima, located south and northeast of the sampling site, and is also near agricultural areas such as Manshat El Kanatir and Bet Rashin, located northeast and southwest of the sampling site. And now, to carry out the chemical characterization step, we analyzed a wide range of PM2.5 components across several collaborating laboratories, including OC and EC, major and trace elements, ions, as well as organic compounds, which were performed at St. Joseph University, where a fully equipped laboratory dedicated to organic compounds is available. And now regarding the results, the PM2.5 average concentration in Cairo was 119 microgram per cubic meter. Out of 59 samples, we had 48 that showed values higher than 80 microgram per cubic meter, which is the Egyptian air quality standard PM2.5 value for 24 hours, and 59 samples showed values higher than the 15 microgram per cubic meter, which is the WHO air quality standard PM2.5 value for 24 hours. And now the next step was to identify the major sources contributing to PM2.5. To achieve this, we used the positive matrix factorization model. This model allowed us to input 24 species and the PM2.5 mass. The PMF data principle consists of a matrix at an input file, including the concentrations and the uncertainties of species. This matrix is divided into 2 output files, the factor contributions and the factor profiles, plus an error. One central question would be, what species should we include in the PMF? In this analysis, we prioritize the inclusion of species that are known to be tracers of sources. For example, cadmium and zinc that are known to be tracers of non-exhaust vehicular emissions, levoglucosan as a tracer of biomass burning, as well as species contributing the most to the mass, such as OC, and ionic species. The stability and reliability of the solution were further validated through normally distributed residuals within the range -3 and +3, high correlation between observed and predicted concentration, successful bootstrap and displacement analysis, and confirming a good model of fit. So the factor profiles and contributions are shown here in this pie chart. So regional pollution resulting from the sum of processed secondary aerosols, mixed regional pollution, and transported crustal dust accounted for 52.2% of PM2.5 mass. Uncontrolled open biomass and waste burning accounted for 22.5% of PM2.5. Industrial sources, including coal combustion, copper smelters, and lead smelters, accounted for 12.2% of PM2.5 mass. Cooking emissions accounted for 7.2% of PM2.5. And finally, traffic emissions, including non-exhaust and exhaust, accounted for 5.9% of PM2.5. Once the major PM2.5 sources in Cairo were identified through the PMF analysis, the next step was to perform the health risk evaluation associated with these sources. To do so, we assessed both carcinogenic and non-carcinogenic health risk associated with PM2.5 sources following the United States Environmental Protection Agency methodology, in which non-carcinogenic risks are considered significant when they exceed the threshold of 1, and carcinogenic risks are considered concerning when they exceed the threshold of 10-6. So these risks were conducted via annihilation by integrating the species in the PNF model that are used in the health risk evaluation that were not originally included in the PMF. For example, the manganese and the benzoapurane equivalent. And as we can see in this figure, the road transport, exhaust and non-exhaust, accounting for 5.9% of PM2.5 mass, largely contribute to PAH-related non-cancer risk and cancer risk with 48% for each. Industrial emissions, accounting for 12.2% of total PM2.5, exhibit a high element non-carcinogenic risk with 38%, and 27% of elemental carcinogenic risk. Open burning of waste and biomass, accounting for 22% of PM2.5 mass, exhibit a considerable PAH-related non-cancer risk and cancer risk with 36%, and regional pollution, accounting for 52.2% of PM2.5 mass, showed a distinct elemental risk profile dominated by mixed anthropogenic and natural sources. The individual lifetime non-cancer risk for PAH was reconstructed to 85% and the elements to 87%, both exceeding the threshold of 1, and the individual lifetime cancer risk was reconstructed for 82 and the elements for 97, both again exceeding the threshold of 10-6. To conclude, this study provides one of the most comprehensive analysis of the chemical composition of PM2.5 in Greater Cairo area and associated sources, as well as the source contributions and their associated health risks. The PMF analysis showed a complex mixtures of 11 distinct emission sources between natural and anthropogenic, and although contributing to 1/5 of PM2.5, industrial and traffic emissions were the predominant contributor of non-cancer and cancer risk. And it's important to note that the incorporation of additional toxic species in the PMF model did not compromise the robustness of the PMF solution. So thank you everyone for your attention, and I would like to thank all the partners in the EMME-CARE project for their financial and technical support.
So thank you, Eliane, for the presentation on Cairo. Any questions? So, okay. So there's a question for you, Eliane. So do you plan to conduct, it's by Ricardo Fonseca, and he's asking, do you plan to conduct a similar field campaign in summer? Do you expect very different results?
So yes, it's important to have a sampling campaign in summer in order to have a seasonal comparison. So we have to compare how the sources change during the seasons. So in fact, we have some sources that will not change because of the season, but we have some sources, for example, that will change. For example, anthropogenic emissions such as, for example, waste burning or industrial emission, they will not be affected, but some natural emissions would be affected and would have higher emissions during summer. That's it.
Okay, thank you, Eliane. So we'll move to the last presentation of this session. It's so from Rimal Abid, and she's from the Laboratoire des Sciences du Climat et de l'Environnement in France, and she will be talking about NOx emission changes from 2019 to 2021 in the EMME region. So Rimal, the floor is yours. Thank you.
Hello, can you hear me?
Yes, we hear you.
You cannot see me though, because I cannot share my camera. I don't know why, but I'll proceed. So my name is Rimal. Sorry. Okay, yeah, I will proceed. So I am Rimal Abid, and my presentation today is about the changes in the NOx emissions in the EMME region from 2019 to 2021. I will first briefly show the method that I use in order to estimate the emissions. Can you go to the next slide, please? So I use an inversion method. The goal from it is to apply corrections to existing emission inventories. In short, I take NOx emission estimates from existing inventories. I take also simulated data from a chemistry transport model, EMME-CARE, and satellite data. In this case, I use TROPOMI, S5P data, NO2 concentrations. And then all of these data sets are assimilated in the CIF framework, which is the community inversion framework, the inversion framework that I'm using. And after multiple iterations that are run through the framework, I get the final corrected result or corrected emissions, which we call the posterior estimates. So on the right, I'm showing an example of a yearly map of NOx emissions for the EMME region with some source regions that I will show in the next slide, please. Yes, so these are some source regions that we will look at. Concerning the NOx sources, Jean Siach already spoke about it, and I guess we have enough knowledge about it, so I'm not going to go into that. Now for the next slide, we're going to see how the emission changes in these regions. So here I'm comparing my results with those from other methods that I use that also use satellite data. This is a method that used, it's a divergence method that used TROPOMI data as well. So on the right, I am showing monthly emissions for the year 2021 for the source regions that I showed before. The dotted lines that are in blue are the emissions before the corrections are applied, and the solid blue line is after the correction is applied. And the pink line are emissions from the TROPOMI divergence method. We can see how our data sets align properly over regions with dominating sources such as industrial or urban sources, but they disagree when there are some biogenic sources. And we can see it also like in the other method how there is a peak and we don't have this peak because our data, our emissions can capture better anthropogenic sources. So go to the next slide. Now we're going to look at how these emissions evolved from 2019 to 2021. In most of the regions that I'm showing here, there has been an increase in 2021 compared to 2019. In the UAE, for example, we can see on the next slide how some of these increase in emissions can be attributed to an expansion in industrial activities. The same applies to Qatar, for example, if we go to the next slide. It also can be related to post-pandemic rise in economic activities. Now, if we look at the Near East, which is Lebanon, we can see in the next slide that during 2019, there was an economic crisis, but following that, there was a rise in the use of electricity generators in Lebanon, and we saw some increase in NO2 concentrations, and as a result also in NOx emissions. Now I'm going to look at national scales. On a national scale, I show here the monthly emissions per country. The mask that I used is also shown in a small plot, and also a bar plot of the yearly emissions per country or per mask. So we can see how in all countries of the Middle East, we see a positive trend from 2019 to 2021. And for the Gulf regions that are in the next slide, in the Arabian Peninsula, we see also a positive trend, except for Kuwait, Oman, and Yemen. So finally, I wanted to see whether some of this increase in emission is related to temperature, is driven by temperature, because we see that some of the emissions of NOx are caused by biogenic emissions as well. And here we are looking at temperature anomalies for Cyprus on the top right. And the NOx anomalies on the bottom, we can see that some of the positive anomalies are correlated, but a deeper study on this is needed. And this is a part of my perspectives that I show in the next slide. So the next steps include improving the inversion that I'm working on right now. I'm working on a third version with different biogenic emissions, so different input data. And I will focus in my future studies on the effect of meteorology on NOx emissions, as well as the effect of the violent conflict operations that took place recently, and the recent war that started in 2023 in Lebanon and Palestine. So that's it for me. Thank you.
So thank you, Rimal, for your presentation. Very interesting, especially during the pre and post pandemic years. So any questions for Rimal from the audience? Please
I can't see any
put them in the chat.
Cannot see any. I don't know if you have any, Sharbel.
No, I can't see any. So, Rimal, I have a question for you about that. So, were you able to check, in fact, whether how much, let's say, the pandemic really during 2020, how much did it really affect the emissions in terms of sectors? So, for example, whether road transport was affected or not, were you able to check like transport, sector level?
No, I haven't done this actually, but it's a part of the post-processing of the emissions. So I will do this for the last version that I'm working on.
Okay.
We can see per second, like we can sectorize the emissions.
Okay, great. That would be really nice.
Yeah.
Okay, so thank you, everybody. Practically, we will, since we're a little bit late, so we will have a 30-minute break, a quick lunch, and so on. Then we will come back and begin again on time at 1 p.m. So like in 30 minutes. So it's 1 and 15 minutes. Okay. PM. So, and we will we will have the new instrumentation and research infrastructure session was chaired by Dr. Diana Francis. Okay, so we'll have a 30-minute break, and we will come back at 1:15 to lunch again and to continue our workshop. Thank you, everybody.
Okay, if anyone would like to share their presentations, just to check, people from the next session. Perhaps Jean-Philippe or Fabian or Eleni, let me know. Marcus, if you want to share, let me know, and I can make you a presenter to check.
Eleni?
Yeah, Chappelle, yes.
Hi.
No, it's fine. It's fine.
Everything okay?
Yeah. I just heard. I couldn't hear you. In fact, it cut a little bit. So, but it's fine. I heard what you were saying. Okay, it's fine.
Okay.
Fine.
Okay, I can see Fabian and Eleni are online. So, Eleni, would you like to go first? Quickly share your screen. Let me make you a presenter.
Can you hear me?
Yes, I can hear you. Yes. Okay, excellent. I can see your screen as well. So
See my screen?
yes.
You can see my presentation too.
I can see that it's opening now. Yeah, perfect. Excellent.
Everything works.
Yes.
Great.
Thank you, Eleni. I'll see you in a bit. I will make now, I can see Fabian's microphone is on, right? So I'll make Fabian a presenter now, just to check his screen as well. And then we'll move on to Jean-Philippe. Excellent.
Okay, can you hear me?
We can hear
Nice.
you, and I can see your slides as well. So.
Okay, perfect. Good. So if I click around, wait, I'm gonna go to presenter mode.
We can see it full screen. Now we can see it full screen as well. Yeah.
Okay, great. Do you see me?
We cannot see you. You will have to turn on your camera, I think.
Share my webcam. Okay.
Yeah.
No? Yeah. Nice. Okay, great.
Thank you, Fabian.
Thank you.
I will now make Jean-Philippe a presenter if you want to try your present. Excellent. We can see your presentation as well. Don't know if you want to try your camera. Excellent. We can see your camera as well. Great. But we cannot hear you for some reason. Oh, wait. It says that you're self-muted.
Here, is that all right now?
Yeah.
So I will speak instead of Jean-Philippe.
Okay. Sorry. Okay, thank you. Good to know. Thank you. So we can see the slides and the cameras. It's good. Can now move on to Marcus, if you want to try your presentation, just to make sure that it works. Don't know if you can hear me. Marcus might not be here. Let's try HJ. HJ, can you hear me?
Yes, can you hear me?
I can hear you and I can see your screen as well. The only thing is I cannot see you yet. Okay, now I can see you as well. Okay, so everything seems to work.
All right, excellent.
Great. Thank
Thanks.
you very much. Thank you. Thank you. And then we can try Damien as well. Yes, okay. Damien, can you hear me? Damien? Okay, maybe not. Okay, great. We'll be back at, as Professor Afif said, we'll be back at 1:15.
Okay, can you hear me?
Oh, I can hear you, Marcus, now. Yeah, excellent. Let me just make you a presenter.
Oh, great, thank you.
Yes. If you want to try sharing your slides as well. Excellent. We can see your screen. Okay, excellent. We can see your slides as well.
You can see them? Okay.
Yes, perfect.
Great.
Great. Thank you.
Perfect. Thank you.
Thank you. Hello, everyone. Welcome back to our workshop. Our next chair is Dr. Diana Francis. Dr. Diana, can you enable your microphone?
Hello. Hi, Eleni.
Can hear you. Unfortunately, because you're in web mode, it seems that there's no way for you to show your camera, but if you can introduce the session and the guests.
Yes.
Thank you.
So we start now?
Yes, of course, yeah.
Yes, okay. Weird, I can share my camera, it's okay. Okay, hello everyone, welcome back. So now we will kick off with the session on new instrumentation and research infrastructure. The first presentation will be by Jean-Philippe Amiet, looking into formaldehyde in air quality networks.
So hello everyone. Is it fine? Can you hear me and do you see the screen? So Jean-Philippe excuses himself. I will present this in place of him. So I will start now. So hello everyone, my name is Audrey Grandjean and I am a research engineer at the company Chromatotech. So I am here to share with you some results with our new instrument dedicated to continuous monitoring of formaldehyde in the air. So formaldehyde is a very highly volatile pollutant. It is formed by combustion processes, by VOC oxidation by radicals, or by alkene ozonation. And since it is very deeply involved in atmospheric chemistry, the European Union included it in the list of recommended molecules to monitor to analyze any trends in ozone precursors. So the standard method to analyze it and detect it is based on liquid chromatography. But it is an offline method that is unsuitable for continuous field monitoring. So we aimed at developing an instrument that could fulfill both the need for continuous measurement, but also at trace levels. So this is an instrument we developed. We called it an EMME-CARE. It is a microfluidic device specific to formaldehyde and based on the Hansch reaction. So the analyzer operates in 3 steps. First, formaldehyde uptake thanks to a trap that allows the transfer of the gaseous formaldehyde from the gas phase into the liquid phase. The second step, the formaldehyde will react with acetylacetone and then form dihydroletidine, which is a fluorophore that is then detected by fluorescence. Sorry, excuse me. So the analyzer monitors continuously within 20-minute long cycles, and thanks to the derivation principle and fluorescence detection, the system is specific to formaldehyde, but also highly sensitive. So this is the type of signal obtained with several examples of ambient air from here 10 ppb to 0.3 ppb. During the 20-minute cycle, the analyzer performs what could be called a blank with pure air analysis, followed by the formaldehyde containing sample analysis. So it will be like a blank analysis, formaldehyde, and then blank again. And this creates a peak that the software can integrate automatically. And the peak area here is proportional to the formaldehyde concentration in the air. So since it's performed this kind of auto-zero, there is no need for offset correction, unlike other existing techniques for continuous monitoring of formaldehyde. So the proportionality of peak area and concentration was confirmed during our laboratory studies. So this graph shows the peak area as function of the concentration in both dry and humid conditions, respectively in black and blue lines here. And the concentration generated to do this test were determined by HPLC using the standard method. So after the laboratory validation and to test it in a field condition, we carried out several field campaign measurements for long periods of time. So 2 were in the countryside near Bordeaux in France at the sea level. They were carried out in winter 2023 and in the summer 2025. And in the summer 2024, the analyzer was placed at the top of the Puy de Dôme at the research station here, which is an extinct volcano at an altitude of 1,500 meters, where we expect cleaner air. During our campaigns, we use the integrated internal standard to check the stability of the system daily. So below here, you see the trend for the daily verification of the 2024 campaign. And to achieve concentration in the target range, we use certified permeation tubes. So here, it generated at 2.89 ppb with an RSD of 8.9%, showing the stability of both the generation system and the analyzer throughout the 3 months of the campaign. So here are the results of ambient air monitoring. The first trend here corresponds to the same 2024 campaign at the top of the Puy de Dôme. We observed a higher formaldehyde concentration in August that decreased towards the colder month here in September. In 2025, which was also in the summer, but at the sea level removal site, the concentration measured here was usually twice as much as for the above campaign, which is consistent with a higher concentration in more polluted areas. So finally, at the same site as here, we have measurements done in winter. And here it was rather rainy season, and the concentration monitored was consistently below 5 ppb. When it rains, the rain usually washes out formaldehyde from the air, and we monitor really only the background noise of formaldehyde. So during all 3 campaigns, the system operated with monthly intervention for reagent refill, and we could observe clearly diurnal patterns even at PPT levels. And also the coverage for data without artifacts was high, so we could process it quite rapidly. So to conclude, we developed an analyzer that was able to measure formaldehyde temporal patterns at ppb and PPT levels. It has a good autonomy, first because it operates with an air generator, 2 because the software can perform automatic data processing, and 3 also it has an internal standard that can be used to check the stability of the system. And also the reagent concentration is quite low, so it only needs to be refilled once a month. The coverage for valid data was high, so it allowed fast data validation and post-processing. And so we concluded that the analyzer has a strong potential for field deployment in ambient air monitoring. So thank you for your attention.
Thank you, Audrey. Okay. Any questions, or we are not taking questions, Eleni?
I can't see any questions. If there are any, they will be in the chat, but there haven't been any for this presentation.
Okay. Okay, thank you, Audrey. We will move on to the next one with with Fabian Schmidt-Ott regarding time of flight mass spectrometer. Fabian, if you are ready, please start. Can you put it please in full mode? You are muted, we can't hear you.
Yeah, now. Okay, I was muted by the organizer, it said. Okay, now you can hear me?
Yes.
Ah, great, okay. Good, so hello everyone, my name is Fabian Schmidt-Ott. Okay, and I'm going to present to you today about some results that we got on the characterization of a high detection sensitivity atmospheric pressure interface time of flight mass spectrometer. So this is, it's a APITOF, also known as APITOF. It's standing in the basement of the Cyprus Institute right now. And basically this APITOF measures very low concentrations at a very high temporal resolution. So first of all, why is it important to measure extremely low concentrations of molecules at high temporal resolution? So for example, we know that for atmospheric nucleation, of course, most of you are familiar with that, molecules cluster to form initial clusters which then grow. And one important precursor gas is, for example, H2SO4, sulfuric acid, at concentrations of around 1 parts per quadrillion. So that is quite low. And this whole process of nucleation can occur quite fast. So high temporal resolutions are important. And then the second example is the detection of explosives, where low volatility explosives are still difficult to detect. And the current detection limit is at around 1 parts per trillion. And of course, also here, a fast detection is needed. So what are factors affecting the lowest possible concentration that can be measured? So first of all, before every measurement with any mass spectrometer, there is the ionization step. So the molecule is ionized, and in order to be able to be detected. And this ionization efficiency is highly variable, ranging from 100% down to 10 to the power minus 5% for some ionization methods. And then the second thing that affects the lowest measurable concentration are the very high transmission losses. So these ions are very diffuse, so the losses are of course very high within the equipment. And it can be up to 99% in APITOF MS systems, or even higher. And a third factor affecting the lowest measurable concentration is actually the method of increasing the signal to noise ratio. So one method of doing that, which is the most common method, is to record as many as possible mass spectra and accumulate both signal and noise, which results in a signal to noise ratio that is proportional to the square root of the sampling time. So the time needed to sample all these many mass spectra. A second method of increasing the signal to noise ratio is the one we used. So using an ion trap upstream the detection stage. So in that way you can accumulate the ions before they reach the detector, and there the signal to noise ratio is proportional to the accumulation time, so which is the sampling time. So this can be more efficient. Okay, so the APITOF we're talking about is the one that is standing right now at the Cyprus Institute in the basement. And this has been produced by Phasmatech some years ago. and it measures in the mass ranges from 28 Daltons to 2000 Daltons with a resolution of 18,000 to 24,000. And the nice thing about this one is it's very easy to attach a DMA in front of it to enable mobility resolved mass measurements. So this is a schematic. I will not go into detail, but the most important part is here, the octuple ion trap, where ions are accumulated before they reach the detector. And these accumulation times can be varied. So coming to the results, so the limit of detection measured for different accumulation times and so for different temporal resolutions. Yeah, it can be seen that the limit of detection decreases almost linearly with the temporal resolution down to values of 10 to the power minus 3 ppq at a temporal resolution of 1 second and 10 to the power minus 5 ppq at a temporal resolution of 1 minute. And note that these are ions, so they have already been charged. So the charging step is not affecting the transmission. Now the transmission of these ions, we saw that the transmission is around 1% or lower. This is consistent with other studies. And the mass resolution goes up to 24,000 for a mass of 1200 Daltons. In a final set of measurements, we also studied the collision-induced fragmentation. So this means that ions are purposely fragmented by letting them collide with other molecules by giving them some velocity. So velocity is given to them by applying a voltage between two segments, between the octupole ion trap and the segment upstream, the ion funnel. So accelerating these ions, they then collide with the surrounding gas molecules, which fragments them. And on the top graph, you can see the fragmentation of tetrapropyl ammonium iodide. And on the bottom, you can see the fragmentation of tetraheptylammonium bromide. So this shows that controlled fragmentation is possible with this epitope. And it also shows that the tetrapropyl ammonium iodide dimer is more stable than the tetraheptylammonium bromide dimer. So in conclusion, accumulating ions upstream the TOF, so the detector, enabled the measurement of concentrations down to 10 to the power minus 3 ppq at a 1 second temporal resolution and 10 to the power minus 5 ppq at a 1 minute temporal resolution. And the transmission is up to 1% for a mass of 600 Daltons. Mass resolutions are up to 24,000. And controlled fragmentation is shown to be possible using tetraheptylammonium bromide and tetrapropyl ammonium iodide dimers. Thank you.
Thank you very much, Fabien. Any questions, please write them in the chat. I don't see for now, so we'll move on to the next presentation. But feel free to reach out to the presenters by email if you have some questions afterwards. So the next presentation will be by Eleni Kolandziki, and she's working on the aerotape instrument to measure and characterize dust aerosols. Please, Eleni, share your slides and you can start.
Can you see my screen?
Yes.
Can you see me?
Yes.
Okay. So hello everyone, my name is Eleni Kolindziki. I am a PhD student at the Cyprus Institute with collaboration with the Califia University and Oberon Sciences, which developed the instrument that I will be talking about today, which is named Aerotape and is a new instrument for real-time quantification and characterization of dust and sources and in general coarse particles. So before I explain more about the instrument, I would like to give some context on the research that I have been doing. So there is a new EU air quality directive which has strict PM10 limits, and it cuts the annual mean by half from 40 to 20 micrograms per cubic meter by 2030, and the daily exceedances from 35 to 18 days per year. But member states are allowed to remove contribution from natural sources such as desert dust or sea salt when they report their values. But this is very challenging to distinguish between local anthropogenic sources like traffic, road dust, or construction, and from regional natural sources, for example, long-range dust transport. And this is all very important to be done in order to have regulatory compliance, to plan for the mitigation, and of course for the health impact assessments. And here is where the need comes for a new instrument that can apportion those coarse particles in an accurate and real time. So now I will explain more about Aerotape. Aerotape draws air through a PM10 inlet, and the particles go and they fall in the adhesive tape on this impactor. Now, the tape moves in a specific step and in a new, very clean background that does not have a sample from before, and then an image is taken by the camera, and the picture that is taken is processed by an algorithm in order to give the particle count, size, color, and shape that is captured from this image. This is made for particles that are approximately from 1 micrometer to 10 micrometer, and it is very important to note that this is very different from the OPCs that use optical scattering in order to derive a size, while Aerotape sees the particles that are taken from the image, and this can be very useful for irregularly shaped particles like dust or sea salt. So now I will talk about the two types of images that are captured by Aerotape. The first image is called lateral, and the light comes from the sides of the instruments and of the instrument, and it has a dark background, which is very useful in order to identify bright particles, for example, like mineral dust. And the second type of images are trans, where the light comes directly beneath from the impactor horizontally, and it has a transparent background, which is very good in order to identify darker particles, which may not be so clear in the dark background of the LAT images. This gives an opportunity to identify and separate particles that look differently, for example, dust, soot, sea salt, and it also gives an opportunity to derive some color information from the images, but I will talk about it more later. So in order to assess the long-term accuracy of Aerotape, we have two campaigns. The first campaign was done in Nicosia, Cyprus, and it started 1 year ago in November 2024, where the Aerotape ran in parallel with the FIDAS 200 optical particle counter. As you can see from the results, the slope of the comparison was 1 and the R-squared was 81, which is very important to highlight considering, as I mentioned before, that they have two very different measurement principles. And this also demonstrates the capability of Aerotape to have long-term measurements and for the imaging system and the impaction, that it can work for a long period of time, and it gives reliable results. Now, for the second major campaign that we had, it was in the port of Limassol, which is very much influenced by marine sources. And this campaign started in July 2025, and the Aerotape was running in parallel with the FIDAS 200 unit as well. From this campaign, we have had more than 2,400 hourly data
in contrast to the daily data that we had in Nicosia, which had also a slope of 1 and an R² of 73, giving an extra good result, because this means that the aerotape does not only work for long-term measurements with daily data, but it can also capture rapid real-time fluctuation that can happen because of traffic, of meteorological driven conditions, and this is very important because we are trying to have real-time measurements to understand better the sources. So now, continuing on the results from Limassol, we see two types of patterns in weekday and weekend results. First of all, we see a peak early in the morning, which is around 6 to 8 local time in Cyprus, which coincides with black carbon measurements from the ethalometer that is also running in Limassol. And this morning peak can be attributed to traffic, because it's happening during the rush hour. And of course, it's only present in the weekdays, not the weekends. And we see a second peak during approximately the middle of the day, which coincides well with a wind speed peak. So this is when we have the higher wind speeds, and this is very consistent during the weekdays and the weekends. So this shows that this pattern is meteorologically driven. So from these results, we can see that the aerotape demonstrates its ability to combine and capture both local, like traffic, and meteorological wind dust-driven influences on PM cores. Now for the last and one of the most innovative tools that we use from aerotape is the extraction of the color from the images. So what we did was extract the orange and red fractions from the pixels using RGB values, and then compare these values to iron concentrations that were measured by exact unit, that is also running in Limassol. And we chose an event that had elevated iron concentration, and we saw that the correlation between both the orange and the red fraction of the color taken by the images from aerotape had a very good correlation, approximately 85 R², with the concentrations from iron. This is very important because it gives the opportunity to have an estimation, a proxy, let's say, of the sample that you get every hour from the aerotape compared to its composition and its mineralogy. So overall, aerotape provides real-time characterization of particles, and it gives information about their count, the size, the shape, and their color. It can capture real-time influences of sources, local, regional, or meteorologically driven, and it also has a very innovative new way of estimating the mineralogy based on the color that you get from the images. So the next plans are to have some multi-city campaigns in Athens, Paris, Cairo, and I'm very happy to report that the campaign in Abu Dhabi has already started in collaboration with Khalifa University, and this is with the goal to build a reference database of PM dust sources in urban environments and to be able to quantify local versus regional contributions. Thank you very much for your time, and if you have any questions.
Thank you very much, Eleni. One question for you. What about the possible identification of nanoplastic particles with the aerotape instrument?
So we haven't looked about nanoparticles because they are way too small, and I don't think that they would be detected from the camera, because as I said, it's approximately from 1 micrometer to 10, and it would need at least a new configuration or a new camera that would be able to capture smaller particles. So not so far.
Okay, another question from François Dulac. Is the campaign comparison with FIDAS? So basically the figure with blue points. Don't you have two different slopes at low intermediate values and at high values? The correlation you showed.
The correlation
with FIDAS. Yeah.
The hourly or the daily? Sorry?
The hourly.
So, as I already explained, the two instruments work in a very different measurement principle. So, aerotape uses an aerodynamic diameter based on the morphology, and FIDAS uses an optical diameter. So, it's very common to notice that the values don't match exactly, but we are just trying to evaluate the accuracy of aerotape in order to go from daily values to hourly values. And yeah.
Okay, one last question for you as well. How well does the elemental composition identification work for other types of particles? For example, how strong is the relation between RGB values and the elemental composition?
So the color proxies that we get from the images is something that we just started looking at because it's something very new. And the first step was to do an analysis on something that we already knew. For example, iron gives this very distinct warm orange-red color to dust particles, and that's why it was chosen as a first proxy. But in the future, we want to try to estimate different color values and shape values, for example, for sea salt and for different types of sources. So this is something that is a goal to be done in the future.
Okay, thank you very much.
Thank you.
Okay, and we'll move to the next talk by, again, the group from Jean-Philippe Amier on multi-system strategy aligned with EU directive for VOCs. Who is presenting?
So I will present in the place of Jean-Philippe Amier. So can you see me and hear me?
Yes, please in full mode and then you're good to start.
So good morning, everyone. My name is Mathilde Mascle and I'm a research engineer at Chromatotech. And today I will talk about the continuous monitoring of volatile organic compounds in ambient air with multiple auto GCFID for the European Union directive. The European Union released a list of recommended molecules that should be measured to analyze trends in ozone precursors. This list includes molecules from various chemical families, such as alcohols, aldehydes, alkenes, terpenes, and others. The analysis of such a wide variety of molecules is an analytical challenge. So the molecule of interest from the European directive are shown here. Chromatotech Hermozone system is designed for VOCs analysis using two auto TD GCFIDs, the HermoVoc C2C6 for the molecules containing 2 to 6 carbon atoms, and the HermoVoc C6C12 for the molecules containing 6 to 12 carbon atoms. And the oxygenated compounds can be analyzed with another GCFID called the HermoOVOC. And the assembly of this system is suited for the monitoring of the molecules included in the list. The three auto GCFID are specifically designed to target a specific group of VOC. That is why each of them is equipped with a specific pre-concentration trap and a specific column for their target analytes. For the HermoOVOC, 3 columns are used. The first step of the separation is for the separation of the polar compounds from the apolar VOCs. And the last column is used for the separation of the oxygenated compounds of interest. And for each system, a flame ionization detector is used. And the use of hydrogen and air generators make the system fully autonomous, which is ideal for field measurements. Hermozone and HermoOVOC systems have been tested on field to evaluate their suitability for long-term online and continuous monitoring of the targeted VOCs. A first campaign took place at the Puy-de-Dôme Research Center, which is located at high altitude. Oxygenated VOCs measurements were carried out from July to September 2024. And the second campaign was made recently in a countryside near Bordeaux at sea level. Oxygenated VOCs and VOCs were continuously measured during 3 weeks from October to November of this year. For both campaigns, the system stability was checked once per day with the use of internal gas standards. The standards are specifically chosen for each auto GCFID in accordance with their target VOCs. So methanol, ethanol, and acetone are the standard of choice for the EMME-VOC, and butane and benzene are chosen for the EMME-VOC C2C6 and EMME-VOC C6 C12. For each system, the internal gas standard is measured once a day to check the stability of the system. For example, the figure here shows the measurement of the internal standard gas of the EMME-VOC during 3 weeks of campaign. And as you can see on the graph, the system shows a very good stability with relative standard deviation below 3%. Oxygenated VOCs were monitored during 2 months at the Puy-de-Dôme Research Center. So the figure here shows the concentrations obtained for acetone, ethanol, and methanol during the month of July. So the systems were able to continuously measure trace level concentrations of the analytes. As expected, the trends of the various molecules are quite similar and follow the temperature variations. They also followed the trend of formaldehyde, which results were presented previously. Oxygenated VOCs and VOCs were monitored during 3 weeks, near a motorway close to the city of Bordeaux. The figure shows the trend of oxygenated VOC for the duration of the campaign. The concentrations detected were mainly below 5 ppb, and 2 concentration peaks of ethanol were detected during the campaign. This result was also confirmed by other analyzers on site, which also observed higher VOCs concentration around the same time. So this confirmed the pollution event in the area. This clearly demonstrates that the system and its 30-minute cycle is able to detect variations of concentration. The figure shows the previous trend on oxygenated VOC compounds, but here we only focus on 5 days, just to see a bit better the concentration variations. OVOCs concentrations measured are usually higher than what was observed at high altitude, and so the system is able to detect concentration ranging from PPT to ppb levels, which makes it suitable for field measurement. The trend on VOC measurement was also obtained, so it is shown here on the figure. This shows the variations of more than 50 VOCs monitored in ambient air. So again, the system was able to detect very low concentrations and occasional increase of the concentration. And here you can see on 24 hours the trend on the BTX compounds, so benzene, toluene, ethylbenzene, and xylene. We see different levels of concentrations, and we also noticed that VOC concentrations were generally lower than oxygenated VOCs. So for 1 day of measurement, we compared the sum of the 3 oxygenated compounds detected, so methanol, ethanol, and acetone, to the sum of VOCs detected on the EMME-VOC C6C12. Which is more than 30 molecules. The graph on the right is obtained, and so we clearly see that only 3 oxygenated VOC represent almost 40% of the detected compounds in ambient air. So this clearly demonstrates the importance of monitoring the oxygenated compounds in ambient air. To conclude, the analysis of such a large group of compounds with diverse physicochemical properties can be challenging. And to answer this challenge, Chromatotech uses a combination of auto GCFID, each of them designed to target a specific group of VOC. The systems were tested during 2 field campaigns. Concentrations ranging from PPT to ppb level were observed. All of the systems were able to continuously monitor VOCs in ambient air. Daily internal gas standard measurement demonstrates the good stability of the systems. And with the use of gas generators, the system demonstrated a strong field applicability for long-term and continuous monitoring of targeted VOCs. Thank you for your attention.
Thank you so much. I don't see any questions for you unless they are coming.
There is one from Garto Fonseca. What caused the ethanol peaks? Do you see peaks in other OVOCs?
So we actually don't exactly know what caused the ethanol peak. So we were monitoring ambient air, outdoor air. So we don't know what caused this. We didn't see any other oxygenated compounds, but there was an increase of other VOCs compounds.
Okay, thank you. Other questions?
No, that was just the one.
Yeah. Okay, so now we move to the next presenter. We continue with monitoring, real-time monitoring of VOC, and now it's with Markus Limger from Austria. Please, Markus, share your slides and start your presentation.
Oh, thank you very much, Dana. I hope you can hear me. So I'm here on behalf of Martin Kraus, who is not available today, but thanks for his greetings. So I'm happy to present the new Sensor. This is our novel solution for recording.
There is some echoes in your voice. Markus, there are some echoes in your voice. Hello? Can you hear us? We can't hear you, Markus. Can you speak? We can't hear you. Hello? Eleni, I think we lost Markus.
Yeah, he doesn't seem to be able to hear us. I can see that his microphone is on. Should we move on to the next presentation and we'll go back to Markus after that, maybe? To give him some time? Okay.
Hopefully the other presenter is here, Joost from Finland. On high resolution multi-pressure chemical ionization mass spectrometry. Please share your slides. Yes, we can see you, but not the slides. Now we can see the slides. Perfect. Can you speak, please?
Right. Can you hear me as well?
Yes, perfect.
All right. So I'm going to talk to you today about multi-pressure chemical ionization mass spectrometry. As you know, when you're trying to, as we've heard during many discussions today or presentations, the gas mixtures of trace gases are pretty complex. They're very chemically diverse, and there's interaction between them that we're trying to understand, especially also in the context of particle formation, secondary organic aerosol formation. And so what our thesis is that multi-pressure SIMS is the best tool to get a full picture with a single instrument. So traditionally, to get pretty broad coverage, you need at least 2 mass spectrometers. You have a charge transfer mechanism like PTR-MS or SIFT-MS to get weakly polar compounds. This is a non-selective hard ionization at about 1 millibar. And then you use ion attachment at high pressure ionization with reagent ions such as bromine, nitrate, or ammonium. This is to get access to the more functionalized compounds. This is a very selective and soft ionization. You have longer reaction times, and due to that, excellent sensitivity. So that happens at ambient. And so normally then you have 2 mass analyzers behind these ion sources to get the broad coverage of chemicals. Now, our idea is to put this in series. So you have 2 ionization regions in front of the mass spec and then you analyze it. So what we use is we use Orbitrap Exploris platform. It has polarity switching and also in less than 1 second. It has actually a built-in low pressure ionization source that's meant for mass calibration, but we figured out that we can use it to ionize the VOCs because it's also at about, these ions get injected at about 1 millibar, and the reagent is actually fluorantine. This source is also called the EZIC source. So it's inside the Orbitrap in the ion optics. These are injected to be used as mass calibration, but they can be used to ionize VOCs. And then in front, we have 2 atmospheric pressure ionization sources in the muon. We call the muon. We use solid state reagents. So we have, for example, solid ammonium nitrate to make nitrate ions by illuminating them with an X-ray. Then the ions are accelerated with these electrodes against the purge flow, so nothing is coming out of the source but the ions, and then they get added to the sample flow, so the sample just gets air being sucked in and getting into the mass spec for analysis, and then we add the nitrate ions for charging, or we turn off the electrodes, which is very quickly in like less than a second, and then we turn on the other source that uses urea for the ionization of other of intermediate functionalized species. So how does this EZIC source work? The internal one, low pressure. Please note that the main ionization mechanism is actually electron abstraction. And not proton transfer. And we hooked up a standard VOC calibration tank and we diluted it, and we see that the detection goes into the PPT range with this setup. And we also assess the humidity dependence of the different species, which is quite similar to PTR, to regular PTR. Now, urea ions are called uranium. It's actually an excellent source. The urea has very nice properties. It's non-toxic and non-corrosive. It has very low vapor pressure, so there's no contamination when the system accidentally shuts down during a power interruption, for example. It's actually a very robust one. It's in a good transmission zone of the mass spec at mass 61. It has a very favorable molecular structure. So these, so up here is the added proton, and these parts serve as pincers that attach to the molecules of interest. The proton affinity is slightly higher than ammonia. It's a very clean source. 99.5% is in the monomer and dimer, which is also a very highly desirable property for chemical ionization to have monomer and dimers. And it's very stable. Here the ion count changed less than 10% over months, and just some milligrams of the reagent will last you for years. So how does it work now when we switch between the different ionization modes? So we alternatively turn one of the modes on and the others are off. So it's not a truly simultaneous measurement, but quasi-simultaneous, because the switching can happen in seconds, and then we switch around. So here you see just outside air from Helsinki from a year ago, where we cycled between nitrate, urea, and the fluorantine, and you see the you see the VOCs like toluene and TMB, the pyridine as a more oxidized species, and then also some of the organonitrates, the highly oxygenated species that we see at very low concentrations just out the window. The nice thing about urea is it's also sensitive to ambient ammonia. Here's a comparison with a tunable diode laser system that shows that they're tracking pretty nicely in the sub-ppb range, and also pretty high linearity. You can see then in the lab, there was a resampled lab air, and we even spiked it a little bit to get higher concentrations. Here are some more measurements from ambient amines with urea. These are the formulas that we find of the peaks, and we think it's aniline, 3-methylamine, and 3-ethylamine. And you can see the traces. You see that they're kind of going up during the day and then back down during the night. So very high sensitivity, very nice performance of urea as a reagent. And here you see, you know, how clean the spectrum looks. You have very high mass accuracy at these concentrations, yeah, performs really nicely, this system. So now when you look at kind of the overall coverage, a typical way to look at this is in these mass effect plots. So you see the VOCs that fluorantinium measures, then the uranium fills up in here, and the more oxygenated species from nitrate. Here is actually, it's plotted versus a function of the oxygen atoms in the analyte. So you see nitrate is at the high end of oxygenation, which corresponds to low volatility. This is the species that are starting to condense and then are responsible for new particle formation. Uranium fills in nicely in the middle, and the VOCs with the low pressure source. One key feature of the system is the high resolution. A lot of instruments these days work with 10 or 20,000 resolution. We've heard before an example. So this is from a real alpha pinene measurement. Here, the 10,000 resolution spectrum is simulated using these three peaks. This is what you would measure. This is what 20,000 resolution looks like. So you start to distinguish two. But you can imagine that fitting this is quite tedious and there's a big effort. This is our measurement with 120,000 resolution. So the peaks are clearly resolved, and identifying them and fitting them is very trivial. And here, even when you go to higher resolution that we can offer, you get clearly baseline resolved peaks. So here a little fun experiment of this fast switching. This is like 8 minutes of data of orange peeling in the lab. So the yellow bulk, which is the limonene, obviously the main thing coming out, but then you can see that there's large amounts of oxidation products actually being formed within minutes in the laboratory, and we can nicely detect them all by switching the reagent modes around and get very broad coverage. So to summarize a bit, Orbion is what we call this whole system. It's a deeply integrated system that has a next generation chemical ionization and a high resolution mass analyzer. And it's delivered with an open source analysis platform that didn't go in this presentation, in the short presentation. We can offer resolving powers between 120 and 240,000. So that gives you clear separation of the peaks and actually allows you to give formula identification with very high confidence. What's the chemical formula of the substances that you're detecting? We've shown subparts per trillion detection limits. So even at these low concentrations, we can very confidently track them. Because of the solid state reagents, there is minimal intervention needed, so that you have very high uptime. Really important is the fast polarity and ion switching. That's automated and gives you then the wide chemical coverage. So from VOCs to amines, acids, and HOMs all in one. Together it's a pretty powerful setup. So if you'd like to learn more, then there is the multi-pressure SIMS is described in analytical chemistry here. The uranium ionization is more described in this analytical chemistry publication. And if you'd like to learn more about the system, there's a webinar available actually on demand. So if you follow this QR code, you will be taken to the registration page. So with that, thanks for your attention.
Thank you very much. Okay, I don't see questions for you for now. Maybe we can switch to Marcus if you're still with us. Marcus?
Hello, yes. Can you hear me?
Now we
Okay.
can hear you. Please
Okay,
go ahead.
very good. Yeah, I apologize for the inconvenience earlier. Today I will present then thank you. Sorry, Martin Gross, my colleague, is not available today, so I am jumping in for him. So I will present the VO Sentinel. So this is our novel solution for automated real-time monitoring of atmospheric VOCs. And so overall, this instrument consists of about a PTR-TOF 3000. This is our platform. So it's a proton transfer reaction mass spectrometer. And it has three main parts. So the first part is our novel in-vion ion source. Here we generate the reagent ions with a very high efficiency of up to 99% for HVO+, for example. And it is possible to really efficiently remove ionic and neutral interferences. And the benefit of this new ion source is that it enables fast switching between selective reagent ions like HVO+, NO+, O2+, and NH4+. The next part is the EVR drift tube reactor. So here the reagent ions are introduced and they mix with sample gas. So then we ionize the volatile organic compounds by means of soft chemical ionization. The conditions in this reactor are controlled so that we achieve a well-defined ion chemistry. And furthermore, this reactor is also using our EVR technology. This is the extended volatility range. So this is a surface treatment that provides very fast response times. And the next stage, the ions are then guided into our time of flight mass spectrometer, where they are separated according to their mass-to-charge ratio. And this instrument uses a resolution of about 4000. So it's a small and compact instrument. And now the important thing about the in-vion ion source is that it allows switching between different ionization modes. So typically we use HVO+, O2+, and NO+. And furthermore, also there's the control of the reaction by applying a drift tube voltage. So the reduced electric field strength, the E/N, can be varied between a high, medium, and low setting. So and then you see here in this time series, the cycling between these different ionization modes. And such a sequence between these 5 ionization modes takes about 1 minute. And the real benefit of these different ionization modes is that it provides much more information about fragmentation patterns and also for specific isomers that they can be separated. So now we switch continuously the ion source, and despite this fact, the long-term stability of the instrument is not affected, as we can see here in this figure. So on top, we have here the time series for acetone calibrations and benzene calibrations in the bottom. And the sensitivity is quite stable and shows only small standard deviations that are well below the ±10% range over a course of 18 days. Another important feature sampling atmospheric air is our feature of the dynamic humidity control. So as we heard, there are compounds like formaldehyde, and these actually have some of them have low proton affinities. And in this case, then they have also strong dependency on the humidity. This can be seen here. When the humidity is increased, the sensitivity towards formaldehyde decreases. And this, of course, affects quantification. Now we actively humidify the sample gas to achieve a stable humidity in the reaction tube. And this then also stabilizes the sensitivity, and we achieve a robust quantification. So the dynamic humidity control provides true humidity-independent detection of VOCs and provides stabilized ionization patterns. Important is also the software. So here we have AME. This is our automatic measurement and evaluation software. This automates the whole measurement by cycling through different ionization modes. And in process, there's also the detector tuning, background measurement, and calibration measurements ongoing. And the data is then evaluated in real time. So we apply averaging, background correction, and peak fitting. But most importantly, there's also the pattern matching algorithm that uses all of these ionization modes for further compound-specific identification. And so the goal here really is to reduce the user interaction and to simplify the measurement. So, and yeah, this all is the VO-Sentinel. So it consists of a PTR of 3000, robust humidity independent gas metrics, a stable instrument, and the quick switching between different ionization modes, and a software that automates and evaluates in real time. Now let's have a look at an example. Isoprene, for example, is an important compound, and in PTRMS, this is detected at mass 69. But then a recent study showed that using a gas chromatographic pre-separation coupled to PTRMS, that in the presence of aldehydes in urban environments, that if they are protonated, then it can also fragment down to the mass of 69, as we can see here. And so in this case, in presence of aldehydes, the concentration of isoprene might be overestimated. The VO-Sentinel does not only have the information from the H3O+ mode, but from all other ion modes as well. And so all these informations were now collected and used to train a peak fitting and pattern matching algorithm. And then we wanted to test this algorithm. And this is the experiment. So we added an amount of 9 ppbs of isoprene. And then this was constantly injected. And then we added spikes of known interferences at much higher concentrations. And we can see that the pattern matching algorithm was able to reconstruct the added 9 ppbs of isoprene. Now let's have a look at an ambient measurement. So here we were collecting ambient data in Innsbruck. This is an urban alpine environment. And we see here the time series of mass 69. Typically, this would be attributed to isoprene. So now we would expect a few hundred ppts of isoprene in Innsbruck. But now let's have a look with the pattern matching. And we will see that actually a lot of contributions arise from different compounds. And the actual isoprene signal is about a factor of 10 lower. And yeah, this demonstrates the power of the VO-Sentinel to accurately quantify compounds and not only chemical formulas. And yeah, with this, I come to the conclusion. So I presented the VO-Sentinel. It is a robust PTRMS analyzer for automated air monitoring, and it provides quality ensured data of a wide range of VOCs from anthropogenic to biogenic sources. A combined pattern matching and peak fitting and different ionization modes significantly reduce potential interferences. And yeah, what's next? So currently we are conducting a long-term measurement campaign at Innsbruck Atmospheric Observatory, which is an ACTRIS national facility. And yeah, we are looking very much to the results. Thank you for your attention. And if you have any questions, please let me know.
Thank you very much. Any questions for?
There aren't any.
No questions?
No.
No. Okay. Thank you so much, Marcos.
Thank you.
So we'll move on to the last presentation in this session from
Hello.
I think we might have lost Dr. Francis.
Ah, so me, I'm here.
So you can go ahead. You can see your screen,
okay.
So you can.
Okay, so you see my screen and I can start. All right.
Now,
so
you can only see the program now. So I don't know if you're using two screens, maybe, or you need to switch to.
Oh, sorry. Does it move? Okay, I think it does change something. Now you see my presentation, right?
Not yet.
Oh, not yet? Okay.
Can see the program now.
All right. Okay, we'll just change to the other screen. Sorry. Here now.
Yes,
maybe it's a presentation.
Presentation.
Okay, great. So today I will introduce a new instrument which has been developed within a European project which is called PurePest, and I will try to show you how this instrument can actually be useful for the Actris network. So within the European project called PurePest, the goal is to identify specific VOCs which are emitted by plants, and especially infested plants. So why is it interesting to actually characterize the VOCs which are emitted by infested plants? It's because the European Union wants to check all the plants that are entering the European Union, just to make sure that they are not infested and they will not bring pests that will actually could damage the culture or the forest within the EU. So the second objective of this project is to try to reduce the amount of pesticide which are used, but especially for the agriculture. And one example of what the pest can do is a picture here of a forest in Portugal, which has been partially destroyed by a pest which has been infested this forest. So here, just an example of few of the pests that are targeted within this European project. And actually, within this project, we start from laboratory studies where we have plants within glass bottles. And we are now trying to evaluate the systems in real conditions to see if it will be used to really check, for example, containers containing plants. So now, what is the link between Actris, VOC monitoring, and this European project called PurePest? Well, you know all that VOCs, they can be produced by biogenic and anthropogenic sources. These VOCs can undergo oxidation to produce OVOCs. These OVOCs are also directly emitted by anthropogenic and biogenic sources. And within this project, we try to identify some very specific VOCs specific from the pest among all the other molecules which are already present in ambient air. So actually, the first goal of this project was to make an instrument which would be sensitive enough and also will allow the quantification and identification of all molecules present in ambient air in order to discriminate the specific VOCs and the VOCs which are already present in ambient air, either in industrial area or in rural area. So for this, we made the evaluation of two systems. The first system was a rack system, and the second system is a portable system, because as I showed during the first slide, the goal of this project is to have a fully portable system which is capable of identifying the VOCs on site. So actually, both systems, they are equipped with the same analytical tools. So in both, we have a pre-concentration unit, which will sample 400 milliliters of gas, and it's equipped with a thermodesorption at 380 degrees C. Again, both systems are equipped with an Apollard column, and they use N2 nitrogen as carrier gas. So for the rack system, usually it's equipped with its own N2 generator, and in case of the portable unit, we will use N2 cylinder. And again, for both systems, we use a photonionization detector, a PID detector, which is heated at high temperature in order to analyze light and heavy VOCs. So first, we made the characterization of both systems, the portable and the rack system, using classical gas mixture. So at the beginning, BTEX mixture, and then we also used the list of molecules which was released from Actris, the list of interest to be followed in ambient air. Again, the goal was to be able to make sure that we can characterize them, just to make sure that they don't interfere with the specific VOCs which are emitted by the plants. So here is another example of gas mixture which is injected to this type of system. So here it's a PAMS system. So the PAMS list is the one list which has been published by the US EPA some time ago. And now we go back to the PurePest project, where we try to identify if the plant is infested or non-infested. So here on the top of this slide, you see a typical chromatogram which is obtained with a non-infested plant. So here we have a mice plant, which is into a glass bottle. We inject 0 air. And here, so we see the non-anal, which is emitted by a plant, where So when the plant is non-infested. Then we infested with a pest, and here we see that we have nonenal, but also another molecule which is called DMNT, which is produced by the infested plants. So here we try to reproduce few times the experiment. So at first you see here at the beginning of the graph, so here on the left hand side you see DMNT in red, and you see, oops, sorry, nonenal in purple. And what we see is that in blank here, blank region, we analyze ambient air, and we see no DMNT, no nonenal. Then we have infested plants in the region which are red. Then we see that both identification are made, nonenal and DMNT. And then when we have an healthy plant only, we have only nonenal, which is analyzed. And so we repeated many times the experiment, and so we see that we have a clear identification of the pest, of the presence of the pest by using VOCs. Now we made the experiment a little bit more difficult. So instead of using one plant into one glass bottle with 0 air, we put few plants into a room, and then we use here a cage just to make sure that the pests will remain actually onto the plants and will not escape. And here we analyze the air of the room, and what we see that again we see nonenal and DMNT, but here a much lower concentration. So here, for example, it's a peak which is about 20 ppt concentration, which means that which means two things. When we want to identify specific VOCs emitted by plants, we need very, very specific and highly accurate instrument. But also it means that this instrument, which is used for this project, can be also very useful to characterize any VOCs at ambient air at very low concentration. Okay, so for the conclusion, within this project, we used a rack and a portable analytical system, which was actually validated for BTEX and PAMS analysis with LDL below 40 ppt for both systems. The rack system has been already evaluated, and it allows the quantification and identification of pest-infested plants in 0 air and also in ambient air environment. And now we are working on the portable unit and to make more characterization with more plants and more pests to see if this will become a powerful tool to actually characterize pest-infested plants. Thank you very much for your attention.
Thank you very much, Damien. Any questions for Damien? We have a few minutes for questions. If anyone has questions. Okay, if no questions, then we close the session. Now it's time for a short coffee break for 20 minutes, and then we'll start again with the next session. Thank you, everyone. See you in a bit.
Bye-bye.
Thank you, everyone. Thank you, Diane. We'll be back at 3, so we keep the order in case some of the participants are not here yet. So we'll have a bit longer of a break, and we should be back at 3 o'clock. Welcome back, everyone. The next session will be chaired by Dr. Tarek Hussein. So, Tarek, can you hear us?
Yes, I do. Thank you.
Thank you very much. I'll pass the floor to you.
Thank you very much. Yeah, just a minute. Dear everybody, welcome back after the lunch. I hope, or after the coffee break, I hope you are doing well. Our next presentation is going to be presented by Ricardo Fonseca. It's about secondary aerosols derived trends and variability of CO2 concentrations in the Middle East during a long-term period from 2014 until 2023. Please, Ricardo, go ahead.
Thank you so much. Can everyone hear me and see the slides?
Yes, we can hear you and we can see your slides.
Okay, so good afternoon, everyone. First of all, many thanks to the organizing team for the opportunity to present work that was done by our team at Khalifa University in Abu Dhabi. We have looked into trends and variability of CO2 in the Middle East, and we have used satellite estimates because until very recently, we did not have ground-based observations in the region. First, a quick overview of our study domain. It's shown on the left. It extends from 20 east to 70 east and from 5 to 45 north, and it comprises mostly arid and semi-arid regions. The figures on the right summarize the large-scale conditions throughout the year. They show the seasonal mean sea level pressure and 10-meter winds. As you can see, the subtropical highs largely control the weather conditions, except in the summer where we have heat low, the Arabian heat low, that develops as a result of the strong surface heating by the sun. So what we did for this domain was to collect all the OCO2 and OCO3 level 2 overpasses, and we bin them into the same grid used in ERA 5, so 0.25 degree grid. From this, we have extracted the seasonal means and looked into the seasonal cycle. We then used a modified version of the divergence method proposed by Liu et al. 2021 to estimate the emissions that go with the satellite-derived concentrations. So this technique works as follows. For a given chemical species X, in this case CO2, you can express your rate of change in this way, where you have your Eulerian derivative, you have the divergence term, then that you can break down into background emissions and sinks, and you have your emissions and sinks on the right-hand side. If you take a long-term mean, and if you ignore the sink terms as CO2 has a rather long lifetime, you can express the emissions in this way, where X and XP are the column CO2 concentration and the background column CO2 concentration that we estimate from the OCO observations. Rho and U are the density and the wind vector that we take from ERA 5 at the closest time to the satellite overpass. We also look into trends using linear regression, and we also use the trend EOF technique that extracts the patterns that account for most of the variability in the trends. So now let's look at the results. Let's start with the seasonal variability. The plots on the left shows the seasonal mean XCO2 for spring, summer, autumn, and winter. This figure shows the seasonal cycle amplitude, and here you can look at the uncertainty. For the majority of our domain, we have the highest seasonal mean values in spring and the lowest in the autumn, with a seasonal cycle amplitude of 3 to 8 ppmv, slightly higher seasonal cycle magnitude values over parts of Southwest Asia because of higher levels of anthropogenic emissions here, especially in the colder months. If you look at the spatial patterns, you can see some hot spots, for example, over parts of northeastern Africa and over parts of the Rub al-Khali Desert. We can at least partially explain them by looking at the emissions and the transport with respect to the background flow. So this is what we obtained from the divergence method. For each season, the blue shading gives the emissions and the arrows give the transport with respect to the background values. If you take Northeastern Africa, for example, you can see that in winter and spring, we have high levels of emissions and a southward transport of CO2, whereas in the summer, when we have rain, vegetation, we have very little transport and hardly any emissions. Over the Rub Alkali Desert, we see some convergence, which may at least partially explain the hotspot we have in the seasonal mean values. Moving on to the trends, this figure shows the column CO2 average over the whole UAE for each month from 2015 to 2022. The trend is around 2.5 ppm per year, which is largely comparable to those reported by other studies for other countries in the region using OCO observations and also GOSAT. For the trend EOF, we found that the first mode accounts for the vast majority of the variance. And here you are looking at the EOFs for each season, and then the respective PCs are given here. The main point to note is this hotspot in the trend around the UAE in the summer, which we attribute to increasing levels of anthropogenic emissions, as given by the EDGAR dataset. We also have higher surface temperatures and sea surface temperatures, with warmer waters reducing the solubility of CO2 into the ocean, so that leads to higher atmospheric CO2 levels. And then we also see a weakening of the wind speed that allows for the buildup of CO2 in the region. We have also compared the CO2 observations from OCO with the forcing data that's used in climate change simulations. So first, we took the raw OCO2 and OCO3 data, and we binned it into the same grid for which the CO2 forcing data is available. And that's shown here on the top left. The x-axis is time in months from 2015 to 2022. The y-axis is latitude from 90 south to 90 north. And this plot goes with this color bar. The other panels show the difference between the CO2 forcing data for different scenarios and the OCO observations for the same period. And they go with this color bar here. In the southern hemisphere, these differences are small, typically 2 to 3, 4 ppmv. But in the northern hemisphere, in particular between 40 and 50 degrees of latitude, where we have the vast majority of the emission sources, these differences can be very large. They peak at 12 ppmv by the end of 2022. We have an up to 30% steeper year-on-year increase compared to the OCO observations, and the seasonality is also twice as large. Now, we made some assumptions when extracting these plots, but they seem to suggest that the CO2 data that's used to drive climate change simulations may be an overestimate compared to the OCO observations. The last thing I want to show is one example of a product that we generate in our team using the WRF greenhouse gas that we run every 4 days for 6 days into the future in the 9 km and 3 km configuration. So we explicitly predict the anthropogenic, biogenic, and the background concentration of CO2, CO, and CH4. And here I'm going to show you one of these outputs from a run initialized on the 28th of July last year. The shading gives the anthropogenic CO2 concentration at the lowest model level, and the arrows give the 10-meter winds every hour starting at 00Z, that's 4 a.m. local time. You can see that during daytime, when we have the sea breeze, we have the dispersion of the CO2 into the desert, whereas at night, when we have weaker winds and a land breeze, we see a buildup of CO2 around the major emission sources and some advection into the Gulf. We are going to use the now available ground-based observations at a site in the desert around here to evaluate the performance of the model. So to conclude, these are our main findings. Feel free to check the paper that we published on this in Frontiers. We have another one on methane, and please browse our team's website to know more about the work that we do. Thank you so much for your attention.
Thank you, Ricardo. Thank you very much. Do we have any questions?
I can't see any questions.
Okay, perfect. So we move on to the next presentation in this session. So we have Alkyviadis Kallisaras talking about the temperature changes due to anthropogenic aerosols over the Mediterranean based on COMIP-6 air system models. Please go ahead.
Yes, thank you. Please confirm that you can hear me and you are able to see my screen.
Yes, we see your screen, but not in presentation mode. Now it's good.
All right,
Yes.
thank you.
Thank you.
Okay, thank you. My name is Alkyviadis Kallisaras. I'm a PhD student in the Aristotle University of Thessaloniki. And today I'm going to present you temperature changes that are caused by anthropogenic aerosols over the Mediterranean basin using COMIP-6 Earth system models. There are a plethora of studies that show anthropogenic aerosols play a major role in the Earth's climate, as they influence its radiative budget and many more aspects of the climate. The Mediterranean region is a hotspot of climate change that has experienced an enhanced warming during the last decades, especially during the summer. And the decrease of anthropogenic aerosols over Europe and other parts of the world have driven temperature changes to the Euro-Mediterranean region. In this work, we assess this amplification of near-surface warming using Earth system models that participated in COMIP-6. We investigate those changes over the Mediterranean basin during the historical period on both annual and seasonal scales. In this work, we used 8 COMIP-6 Earth system models, which are presented in this table, and to evaluate, to quantify changes in the effective radiative forcing and near-surface temperature. We used historical simulations that were run by the Earth system models presented here. And each of these climate models produced two sets of identical simulations with same historical forcing, except one used fixed pre-industrial anthropogenic aerosol and aerosol precursor emissions. So by subtracting those experiments, we sort of isolate the effects of anthropogenic aerosols on the Earth's climate. And here we see changes over the Mediterranean region throughout the historical period. On the left column, we see changes in aerosol optical depth. We see that it peaked around the late 1970s to early 1980s over Europe. And likewise, the ERF reached its most negative values around the same period on an annual basis. And as we can see, the evolution of both trends is more significant, is larger in magnitude during the summer. Here we see the spatial pattern of changes in transient ERF at the top of atmosphere. We see that during the peak anthropogenic aerosol period, which is 1970 to 1979, anthropogenic aerosols caused surface cooling. But after the anthropogenic aerosol removal over Europe and North America mostly, we see that we have positive values of ERF, which are linked to surface warming. Here we see the evolution of temperature over the Mediterranean region. On the left figure, we see changes that are caused by anthropogenic aerosols only using the CMIP6 experiments. We see that around 1975 to 1980, we have a minimum in temperature changes, negative temperature changes, and then the trend goes to, and then there is a positive trend indicated by surface warming. And on the right figure, we see changes over the land, and we see that the temperature change that is produced from the Earth system models is in agreement with observational datasets, and anthropogenic aerosols are responsible for almost half of the annual warming between the two periods, and for almost 40% of the summer warming observed in the region. However, in the winter, climate models produced an overestimated warming, and anthropogenic aerosols contribute roughly 60% to this warming. And this is the spatial pattern of temperature changes. There is a peak in the surface cooling over Europe and the Mediterranean during the peak anthropogenic aerosol period. And after the aerosol removals, due to air pollution policies, we see a surface warming over the Mediterranean, mostly over the Eastern Mediterranean region, which is robust for the majority of the climate models used here. And here we see circulation changes that contribute to the changes in temperature observed, simulated, in the Mediterranean, along with radiative effects. We see that cyclonic anomalies that are induced by anthropogenic aerosols on annual scale and during the winter, this is after the aerosol removal on the right column, could be responsible for a warm advection from the northern parts of Africa, and anomalies over the Eastern Mediterranean in the summer could also contribute to the amplification of the surface warming over the eastern parts of the Mediterranean and southeastern Europe. To conclude, we see that the effective radiative forcing and near surface temperature exhibit decreasing trends around the late 1970s to early 1980s, which are followed by increasing trends, mainly due to air pollution control policies over Europe and North America for the most part. And overall, we see that the ensemble shows a robust amplification of the surface warming over the Mediterranean basin on annual scale and during the summer. due to global anthropogenic aerosols reductions, which is in good agreement with observational datasets over land grid points. And we also saw that circulation changes that are induced by anthropogenic aerosol reductions play an additional role in the redistribution of regional surface temperature changes apart from the radiative effects. These results are summed in our recent publication, which is a preprint for now. You can check it if you want. Thank you very much.
Thank you very much. Do we see any questions?
No question.
If there are no questions, then we move to the third presentation, which is the last in this part, remote sensing atmospheric climate modeling. So the next one is by Konstantina, talking about machine and deep learning approach for statistical downscaling of COMEP6 climate projections. Please go ahead.
Hello, can you hear me?
Yes, we can hear you.
Can you also see my presentation?
We don't see anything yet. Can you try again, please?
Okay, just a second. No. I think I don't have the permission from my computer to share the screen.
I can share it.
Do you need to log out and
I can have the presentation, so I can share it on behalf of Konstantina.
Okay, thank you, Lenny. Thank you. Good afternoon. My name is Konstantina Koudroumanu. I am a PhD student at the Cyprus Institute, and I have a joint degree, so I also have a collaboration with the National and Kapodistria University of Athens. And in this presentation, I will show you how we can use machine and deep learning models in order to statistically downscaling the COMEP6 climate projections to the urban scale for Nicosia city. Next slide, please.
Because it doesn't really show it for me.
We do not see the slides very well, I think, Elioni.
Just a sec, I'll try sharing them again.
I can't see anything.
There is an issue with the way it opens, but give me a sec, I'll try it again.
Okay.
For some reason, it doesn't let me open it properly. Perhaps we can move, Tarek, can we move to the next presenter until I sort it out?
Okay, so we start with the next part of this session. All right. So we come back to this presentation by Konstantina, but now we move to the next part, which is within the title Atmosphere and Climate Modeling and Prediction. So our next speaker is Franco.
Can you hear me?
Doctoral network. Yes, we can hear you and we see your screen.
You see my screen?
We see your screen and hear you, but we...
Perfect.
Yeah. Okay, good. Now it's perfect. Everything is perfect. Franco, go ahead. Yes.
So, thank you very much for having me here. I'm very honored to present to you a project made of several projects, which is called the Dust Doctoral Network. It's funded by the Marie Sklodowska-Curie Actions. It's all centered around dust, and you can see on this slide that there are a number of contributors, which I'm not going to name one by one, otherwise it would take the whole time of the presentation. What's happening here? Start changing slides. Okay, so dust, let's remind us a bit of what dust is. Dust is emitted by the wind in the desert areas, and it's blown by the winds. It's also transported by the winds, so the winds have often an effect on the dust. Transported, it can travel several thousands of kilometers, something sometimes people don't realize how far it can travel. And during this travel, it will undergo a number of processes with the interaction with radiation, direct forcing through a scattering and absorption, and also interaction with the humidity fields to act as cloud condensation nuclei or ice nuclei. And then dust will at some point fall back on the surface through deposition, dry deposition, wet deposition, and then will fall on the surface, will have an impact on the biogeochemistry, on the ocean, and then when it falls on the land, it will interact with human activities. So the dust yen, that's how we call this project, has 4 research objectives. The first one is around the fundamentals of dust properties. The second one is about the influence of source regions. The third one is about socioeconomic impacts, and the fourth one is about dust in the global climate system. And you can see the map on the screen that shows the partners in the project, with a large number of them in Central and Western Europe, and a tail towards the southeast, with the Cyprus Institute, which is the coordinate, which I'm representing here. So how does it work? We, under each of these, how do you call them, research objectives, we have a number of PhD projects. So the first one, if I remind you, the first research objective was about the fundamentals of dust, and we have here 5 PhD projects. The first 3 are actually all around the particle shape. Then we have one which is about turbulent transport of dust, and the last one about ice nucleating properties of dust. We then have a second research objective on the source regions, and here we have 4 PhD projects. One of them is a modeling project, but the other 3 are observational projects based on different techniques and all of them want to characterize how the source regions interact with the dust properties that we measure downstream. The third of these research projects is about socioeconomic impacts. And here we have, again, 4 PhD projects, each of them addressing a different impact. So the first one is about air quality policy. The second one is about aircraft engines. The third one is about how dust affects the solar energy production. And the last one is about the respiratory health impact of dust. Finally, last but not least, the fourth research objective is about the global climate system and the interaction with dust. And here again, we have 4 projects. 2 of them are modeling projects, but 2 of them are observational projects. Now, by putting together so many partners in the project, we also put together a lot of facilities that we use for this research. We have 3 high-performance computers with state-of-the-art models. We have a UAV facility in the Cyprus Institute. We have a number, I'm not going to name them all one by one, but we have a number of ground-based observatories, either remote sensing or in situ or both. We have an electron microscope center. We have a particle sensing laboratory. We have a couple of solar energy production facilities, and we have a couple of biocell culture exposure, how do you say, biology laboratories to study the impact on health. In addition to the facilities that I just named, we will also leverage on novel space missions, and namely the EMME mission, which was dedicated to dust and then dust sources, and the EMME-CARE mission, which is dedicated to the 4-dimensional distribution of aerosols, clouds, and radiation. And you saw our some presentations this morning from people taking part in the network. So we had the network started operating about a year ago, and the first students started their work about 6 months ago. So we have already, as I said, first campaign here in Cyprus with several instruments. On the left-hand side, we can see our remote sensing instruments. On the right-hand side, we can see some collected dust samples with different methods. We also have first modeling efforts at the Barcelona Supercomputing Center. Here, in particular, the objective of the slide here is to show that the model is reproducing the observations. And we also started working on the satellite data with some first, let's say, familiarization, validation using ground-based instruments, but with the aim to be able to talk about the 4-dimensional global dust distribution. So it's a great educational scientific project with 17 visionary PhD projects embedded within it. It will enhance collaboration between the partners. It will advance, I hope, in a memorable way, the science of atmospheric dust, and it will train the dust experts of tomorrow. Again, that's the intention, that's the hope, and I'm sure that will be also the outcome. Just before I finish, a quick announcement that we have the DustDN network will have its workshop in a few months here in Cyprus. And so please, if you're interested, feel free to submit an abstract. Actually, we have a very short deadline. It's on Monday, if I'm not wrong. So, but it's very simple to submit an abstract. It doesn't require a lot of effort. So if you're interested, please do. And that's all I have to say. Thank you very much. And I'm happy to take all your questions.
Thank you, Franco. Do we see any questions, Leonie?
I cannot see any questions. No. Franco, if you would like to share the link for the workshop as well in the chat, so if people can go directly to the workshop information, if you like.
Yes, I'm not sure. Do I have a chat? Yes, I couldn't see a chat before.
Or I can share it if I find it out.
Yeah, the chat here. Yes. Okay. I will do that.
Okay. Shall we go to the next presentation by Antonia? Exploring the...
Back to Constantina. Sorry, apologies, Tarek. Can we go back to Constantina because she's connected again, so we can...
Okay, if Constantina is ready, we can go back to Constantina. Yes, go ahead, Constantina. Please go.
Constantina, can you hear us? If you can hear us, you're self-muted, so you will need to unmute yourself.
Can you hear me now?
We can hear you now. Yeah, perfect.
Thanks, God. Can you also see my screen?
Yes.
We see your screen, but not in the presentation mode.
Okay, I will fix it now. Just a second. Maybe now?
Yes, now it's perfect. Go ahead. Yes.
So as we already know, the EMME region is a climate change hotspot because it warms faster compared to the global average. And also we know that summer temperatures are increasing even faster than the annual means. And in cities, this is further intensified by the urban heat island phenomenon. And also this intensification has strong implications for different sectors like human health, energy, systems, economies, etc. Especially in Cyprus, we know that rising temperatures are directly linked to increased heat-related mortality and hospital admissions. And also from long-term records that we have, we know that we have a temperature increase of about 0.5 degrees of Celsius per decade in summer and spring. So the global climate models that we have, we know that they have a very coarse resolution, and therefore they cannot capture the urban scale processes. And for this reason, we need to use downscaling techniques like the dynamical or the statistical in order to downscale the global climate outputs to the urban scale. And here we can see a comparison between the dynamical and the statistical downscaling methods. Usually with the dynamical downscaling, we use regional climate models in order to dynamically downscale the climate at finer scales. But the main drawback that we have here is that they are very computationally expensive. On the other hand, we have also the statistical downscaling. And here we build statistical relationships between the large-scale variables that are called predictors and the local-scale variables that are called predictants. And this process is much faster and more flexible, but we have the main drawback that it assumes that these relationships that we extract between the scales will remain stable over time. So the main research objectives of this study are, first of all, to develop a cascade modeling framework that will link the global, the regional, and the local scale with a focus given on Nicosia city. We also want to apply both downscaling techniques, the dynamical using the WRF model and the statistical using machine learning models that will be the multiple linear regression, the artificial neural networks, and the convolutional neural networks. And we also want to compare the efficiency of both methods in reproducing the maximum and minimum temperatures. And finally, we want to assess how summer temperatures in Nicosia are projected to change in the future. So here we can see which is the overall workflow from the dynamical and the statistical downscaling. And regarding the dynamical downscaling, we use the WRF model driven by the CMIP6 data during the historical and the future period. For the future period, we use the data from the SSP2 scenario. And therefore, we had some outputs for Nicosia city at 1 kilometer spatial resolution. And on the other hand, for the statistical downscaling, we used the WRF model again, but for this case, we used the RFI data for the historical period in order to downscale them to the regional and the local scale. And with this method, we had the databases that we needed in order to extract the statistical relationships between them. And we used the regional data from WRF model driven by the CMIP6 and the statistical relationships in order to produce some statistical outputs from the 3 different machine learning models at 1 kilometer spatial resolution.
And here we can see which was the WRF configuration. We used the WRF model coupled with a single-layer urban canopy model, and also we created a land-use, land-cover classification map that was combining the Korean global land cover, the MODIS, and the local climate zone datasets in order to have a better representation of the urban morphology of Nicosia. The WRF model had 3 nested domains over the EMME region, over Cyprus, and over Nicosia. And for the evaluation of the model, we used meteorological data from the Department of Meteorology of Cyprus, but one station only, Nicosia station, because it was the only one which was urban and it was located within the D03 domain. And here we can see on the left the 3 nested domains. On the top right, we can see the D03 domain as a satellite map image. And on the bottom right, we can see the D03 domain after the classification, the land use, land cover classification map. And we can see that for Nicosia city, we have only 4 different local climate zones, 3, 6, 8, and 9. And here we can see the configuration of the machine learning models. We use the perfect prognosis approach because we used the R5 data in order to extract the statistical relationships, and the R5 data have a day-to-day correspondence. And for this reason, we can say that the relationships that we build can be applied to any climate models. Also, we used predictors from the surface and the upper atmosphere also, and the data were split in 2 parts, the training periods and the test period, where we want to evaluate their performance. And then these relationships were applied to a historical and a future period, but from the CMIP6 data. And here we can see a map that shows the annual average of Tmax, which was produced by the WRF model and the other 3 statistical models. And we can see that the machine learning models can reproduce the spatial patterns of the WRF with a very good accuracy. And here we can see the similar maps, but for the minimum temperature variable. These maps are only for the test period for the year 2012. And here we can see the performance of the different machine learning models that we used compared to the WRF outputs for the maximum and the minimum temperature. And we can see that among the different machine learning methods, the convolutional neural networks had the best performance, particularly for the maximum temperature, which indicates its ability to capture complex spatial patterns. And this suggests that deep learning can complement traditional dynamical simulations, especially when computational resources are limited. And here we can see the projected summer temperature changes for the future conditions from the WRF outputs, but also from the 3 statistical downscaling techniques. And on the right, we can see the ensemble mean from the 4 methods, and we can see that we have an increase of approximately 2 degrees for the maximum temperature. And here we can see the respective maps, but for the minimum temperature variable. And here we can see that the ensemble mean of the future summer change is of 1 degree, is around of 1 degree. So to conclude, we can say that both dynamical and statistical downscaling techniques improve the resolution of the CMIP6 projections to the urban scale. Also, the WRF model provides physically consistent simulations, but the machine learning model approaches were able to reproduce the WRF model, and this indicates that they have a very strong predictive skill, and they have a very lower computational cost. We can say that among the statistical models, the CNN had the best performance, especially for Tmax variable. And we can also say that this combined framework supports robust high-resolution climate projections for EMME cities contributing to better heat mitigation and adaptation planning. And thank you for your attention.
Thank you very much. Do we have any questions to Constantina?
There are two questions in the chat. The first one is from Ricardo Fonseca. How do ML models perform for extremes? Have you also looked at fields like precipitation?
They are very good to simulate the extremes, but we haven't checked the precipitation yet.
Thank you. And the second one from Shmuel. I want to ask if integration single layer canopy model can be good for large cities like New York, London, or Beijing.
There are several studies that compare the different urban models that can be integrated with a WRF, like the single layer that we used and the BEP plus BEM, which is more detailed. And they show that they are different. So you should do some sensitivity analysis with the two different models in order to see which of these two is better for your case, like the New York City. But in general, when you have a very big city like New York, and if you have low computational resources, I think that the single layer is better.
Great, thank you, Constantina. Tarek, I think we can move to the next presenter.
Okay. So we go back to the climate modeling and prediction with the second presentation by Antonia.
Yes, can you hear
talk
me?
about exploring the serious game, what's going on in the air. So please go ahead. Let's see.
Can you see my screen?
We don't see anything. Now we see.
Yes, you see the presentation?
Not in the presentation mode. We see the PowerPoint slide.
Now?
No.
Yes?
No.
Now?
No.
I think now we will change the display settings at the top, because now we can see your notes in the next slide. But if you, the middle button, the parameters in the middle, if you change those to duplicate your screen, we should just be able to see your slides.
So, monitor.
Now it's perfect.
It's okay? Okay. So, hello. My name is Antonia Zoka, and I work at the National Center of Scientific Research in France. I did my PhD in atmospheric science, followed by a standard postdoc. But over time, I realized that I also love teaching and the development of innovative and creative educational tools for atmospheric science. So my presentation today is focused on a serious game that we have developed with my colleagues this year. And its name is What's Going On in the Air. Okay. what comes to your mind when you hear the term serious game? So the concept of gamification is widely used in education to increase student motivation and engagement. A serious game combines the concepts of gaming and training. Like a game, it provides an opportunity to have fun and to feel engaged with the proposed interactions. It has rules and an educational scenario that transform passive learning and fostering a deeper understanding. It is a serious game because it is based on real-world events, or real case studies that develop the critical thinking. The serious game, What's Going On in the Air, bridges the gap between complex atmospheric research and training opportunities, providing an interactive way to discover aerosol science and remote sensing under real data and in a simulated environment. The player takes on the role of a young scientist who has just joined the Atmospheric Observatory of Lille in France. In particular, the aerosol remote sensing group of the observatory ATOL. Their mission is to investigate a real aerosol event over 2 virtual days. Mona is a scientific expert from the French National Center for Scientific Research. She serves as a mentor figure, asking questions and encouraging the player to critically apply his atmospheric science knowledge. Max, the technical support staff member, offers practical assistance by providing key explanations and hints related to the operation and the understanding of scientific instruments used during the game. The serious game is designed to provide basic knowledge about aerosols through short interactive exercises like this one you can see here. Then, progressively, it introduces the principle and instrumentation of sun photometers and LiDARs, helping players build a strong foundational understanding. To support the non-expert players, this progressive approach includes instrumentation descriptions and basic theoretical knowledge are organized in a virtual pad, as you can see the menu of the pad here. So the scenario encourages the player to apply that knowledge to a real-world atmospheric situation. The players learn to identify different aerosol types and their origins through back trajectory analysis. They can also develop the skills needed to interpret atmospheric scatter profiles from real LiDAR data collected at ATOL Observatory. The game enables the player to deepen their understanding of the interpretation and combination of LiDAR and sun photometer data. And finally, they call to estimate the aerosol mass concentration. All of this, of course, while working with real data from LiDAR and sun photometers. Apart from the multiple choice questions and the activities, the game also includes additional tools, such as a quiz and a mini game, to give extra motivation to the players. Regarding the evaluation and scoring, correct answers to the scientific questions and activities contribute to the total score, while the maximum achievable score is 32 points. The series game is currently available in English, open to everyone, and it takes about 40 minutes to complete. It is targeted at undergraduate and graduated students, early career researchers, operators of research infrastructure facilities, and professionals. It also appeals to a broader audience interested in quality and climate change. To summarize, the main educational objective of the series game What's Going On in the Air is, first of all, to provide accessible, effective, and free learning in atmospheric science. Also to introduce the fundamentals of aerosol science, teach the interpretation of atmospheric remote sensing data, and foster problem-solving skills in a realistic scientific context. The scientific content was created by Véronique Riffaut and myself with the scientific expert help of Philippe Golub and Ioana Popovic from Atoll Observatory. And the technical support, we have really technical support from Marc-Olivier Buisson and Gaël Guigon. So it was a teamwork. In conclusion, at our department at IMT, we are trying to move education beyond passive reception towards active engagement and deeper understanding through powerful innovative tools. We have successfully developed 3 massive open online courses, MOOCs, focusing on critical atmospheric issues like air pollution causes and impacts, atmospheric research infrastructures, and we have a new course on air pollution processes and characterization that is coming on. Furthermore, within the ATMO-Access project, the framework of the ATMO-Access project, 3 tutorial videos were developed, providing hands-on guidance for advanced instrument functions, data analysis services, and platform navigation using real case studies. Finally, as discussed, serious games like What's Going On in the Air and another one, the Smellville, immerse students in realistic scenarios, providing a unique learning experience. All these innovative tools are designed to be long-lasting and to contribute to economically and environmentally sustainable education. Initial feedback from players has been overwhelmingly positive, demonstrating the game's success in providing a unique, effective, and enjoyable learning experience. Looking ahead, we are also working on a new version of this game with a more advanced level and a more beginner's level. And we invite you to take the chance and learn while having fun. Thank you.
Thank you very much. Do we have questions? I think we are running out of time. We are late, maybe 5 minutes, right?
Yes, yes.
Okay.
To the last presenter.
To the last presentation by Elias in this part of the session, identifying keystone plant species involved in rainfall induction. So go ahead, Elias.
I will share his slides and he will be with us, hopefully. Elias, can you?
Okay, so you are.
Yes.
Hello, can you hear me?
Yes.
My name is Elias Anastasopoulos. I am professor of biotechnology at the University of Thessaly, that's central Greece, and present the work we did together with Serafim Papadopoulos for identifying keynote plant species involved in rainfall induction. The aim of this research is to fill in some knowledge gaps related to the hydrological cycle and by precipitation in particular. Can I have the next slide, please? More or less the relationship between rain and vegetation is, I believe, known to everyone. What we will see together in the next slide is the bioprecipitation phenomenon, which is the role of bioaerosols. This is what we are studying, particularly pollen, in cloud formation and in particular in orographic cloud formation. May I have the next slide, please? So it is already known that these bioaerosols that affect cloud formation may be either fungal spores or bacteria, particular of the genus Cyanomonas, or pollen. These are the more frequent ones. But we don't know exactly what type of pollen and what type of plant species produce the pollen detected in the clouds. May I have the next slide, please? So what triggered us to this type of research was the fact that despite that the flowers are the most sensitive organs of plants, susceptible to freezing, there are some winter flowering plants. So we try to understand the biological role of these plants. May I have the next one? So in regard of the keystone species terminology, there are three types of generally recognized as keystone species, either predators, mutualists, or ecosystem engineers. So we are referring to the last class, ecosystem engineers, where an ecosystem engineer is an organism that creates, changes, or destroys a habitat. Can I have the next slide, please? So we propose Crepis sancta, a cosmopolitan species belonging to the Asteraceae family that is abundant in all continents. And you can see this is from our campus in Larissa. That's a football field which is covered by this model plant for studying bioprecipitation that opens and closes the flowers depending on the cloud, on whether it is a cloudy day or not. So when they reach a certain level of energy that is transferred from the sun to the flower, for example, a total 3 hours of sunlight gathered, then they close. May I have the next slide, please? So by using a technological platform that we have developed in-house that consists of an circulating alcohol bath, a laptop, and an infrared camera, we have managed to measure the freezing activity of pollen grains among other biological samples. May I have the next one? So we have built up a particular software for this reason, which is called Microthermalizer. Actually, this is a video, but I think we can skip that and go to the next one. So the aim is of this platform is to continuous monitoring and data recording of freezing events and their interactions. And we have gained a lot of data that refers to pollen grains. Here we can see flowers from the Crepis sancta, and on the right, the pollen of the grain. May I have the next one? And this is an IR photograph from the flowering that we wanted to measure the flowering time. May I have the next one? If you can press on the left side of the black bar, yes, you can. Yes, I think it's thank you very much. You can see that this pollen grain, which is from Crepis sancta, bursts, and this is very important because not all species have pollen grain that bursts when they get water. The ones that they do, they are also, this is very important for the people that develop allergies, particularly after thunderstorms. This is well known. So we have two qualities that we are looking for in a plant, so that to relate that with bioprecipitation and rainfall induction. The one is the ice nucleation, which is measured by the technological platform I just presented you, and the other is the pollen bursting activity. May I have the next one? So what we are looking for is collaborations, particularly with people which are interested in pollen sampling, and they can quantify the pollen so that we can collect pollen from various parts of the region and test for ice nucleation activity and pollen bursting, which are the two qualities we are looking for in order to determine whether a plant species is related with the cloud, orographic cloud formation. May I have the next one? So, as I said before, we are also looking for students and young scientists from the EMME region who would like to be trained in our labs and gain valuable hands-on experience in bioprecipitation. Thank you very much, the organizers, for letting me having this presentation. and Eleni for sharing the slides.
Thank you,
Thank you,
Elias, for
Professor
presentation.
Hussein.
Thank you. Do we have any questions, Elioni?
I cannot see any question. There is one by Ricardo. Interesting talk. Why is bioprecipitation more relevant to orographic clouds, as you mentioned? Is it because it is more effective as ice nucleating particles?
From what I have understood from collaborators from atmospheric scientists, they say that because of the winds, that when it passes through areas with vegetation, then it's uplifted to the top of a mountain. And this is how it helps the orographic cloud formation. I'm not aware of other types of clouds that are related with bioprecipitation.
Okay. So no more questions?
No, that was the only one.
Then we come to the end of this session, and I will leave the floor to the organizers to come to the end of the scientific workshop. Thank you very much.
So thank you, Tarek, and thank you for all the attendees. Hope this day was very useful and interesting for you, adding more knowledge also to and ideas to your research. Thanks for everyone, for the presenters, for the attendees, for all the people also that were involved in the preparation of this workshop. Thank you, Eleni, and Marina too. That would be all for this year, and so hope to see you also next year for the fifth version, for the fifth workshop. And hope definitely, I think you will also attend this event. So any other thoughts, Eleni?
Thank you, Charbel. Thank you again to all the speakers, the chairs and attendees, and you, of course, for all your hard work on this. And see you again next year.
Thank you. So bye, everyone.